Algebra of functions and function composition. In this section, we're going to learn different ways to combine functions to make new functions. Let's start with this definition. Let f and g be two functions with domains d sub f and d sub g respectively. So d sub f is the domain of f and d sub g is the domain of g. We're going to define the sum, the difference, the product, and the quotient functions based on these two given functions f and g. Okay, so the first way we're gonna combine the two, we're gonna add them. The second way we're gonna take the difference. The third we're gonna multiply, and the last one is we're gonna take the quotient. Okay, and the way these functions are gonna operate is very similar to the way we usually add, subtract, multiply, and divide numbers. Okay, so let's take a look at the first one, f plus g acting at x. So the value that the sum function f plus g takes on that input x is equal to the sum of the respective values that x takes when f acts on it and when g acts on it. Okay, so the notation here, f plus g, allows you to anticipate the kind of output you may get. The sum of functions acting on an x is equal to the sum of their respective outputs. Okay, sure, this side which is the right hand side is defined as long as each of these two entities is defined, right? So if f of x makes sense and g of x makes sense. And when does f of x make sense? If x is in the domain of the function f, right? For this output f of x to exist, you need x to be in the domain of the function f, right? So condition number one, I need x to be in the domain of the function f. How about this? For this guy to exist, you need x to be similarly in the domain of g this time, right? So conditions 1 and 2 allow you to say that the sum is meaningful, and hence this guy, which is defined as such, is meaningful. So x has to be in the domain of f and x has to be in the domain of g, which means x should be in the intersection of the two domains, d sub f and d sub g. Okay, remember this notation. This means the intersection of the two sets, df and dg. Okay, all right. And the others are going to be very similarly defined. So the notation actually lets you anticipate the kind of output you may get. So f minus g, this difference between the two functions, when you input x in this function, it outputs the difference of the two functions of the outputs of the two functions when the input is x. Okay? And similarly, this side makes sense as long as f of x and g of x exist, which means x should be in the domain of f and x should be in the domain of g, so you get that. And the product f times g, the value it takes at x is the product of the respective values, right? F of x times g of x. And likewise, this product exists as long as each of the two entities exist. The first one exists if x is in the domain of f, and the second one exists if x is in the domain of g, so x should be in the intersection again. Okay? And lastly, the quotient f over g acting at x is equal to the quotient of f of x and g of x. And this quotient exists provided three things happen. You need the numerator to exist, which means x should be in the domain of the function f. You need the denominator to exist, which means x should be in the domain of g, right? And the last one is that you need the denominator not to be 0. Okay? So for all x which are in the domain of f and in the domain of g, such that g of x is not 0, this quotient function is going to be meaningful. Okay? Alright, so let's go to the book and start with some problems. This is section 1.8 on page 224. Let's start by one of these problems from 5 to 8. So we're gonna find the sum function of f and g are given in each problem, and identify the graph of f plus g. Let's say 8. The function f of x is x squared and g of x is 3. The question is, what's f plus g? Okay, so this is the problem. So that's on page, as we said, 225. Okay, so this is the problem, and we need to find the sum function f plus g. Well, f plus g, by definition, the sum of those two functions f and g acting at a point x. How is it defined? How is it defined? It's just the sum of the outputs, right? I mean, one point of reference here is this sum here is at the level of functions. This sum here is at the level of numbers, okay? So we're defining the sum of two functions based on our knowledge of how to add two numbers, because this is a number and this is a number, right? So this sum is at the level of numbers and this sum is at the level of functions. We're defining this to be as such, okay? So this is how we are combining the two functions f and g. Similarly here, this minus is at the level of functions and this minus is at the level of numbers, and similarly for the rest, okay? Okay, so what I wanted to do here, I wanted to appeal to the definition and try to see how this function operates. Well, it operates by just adding the outputs of f and g. So we get f of x plus g of x, and here this is simply definition, right? This is simply by appealing to the definition. This is how the sum is defined. Okay, now in my context, what's f of x? F of x is x squared, right? This is the output of x under f, that x squared, plus g of x is 3, right? Okay, so what's this function? What's the sum function? The sum function is simply x squared plus 3. Okay, now the last part of the question, how do you graph this? They gave us about 4 graphs, I think, and the question is, which one is it? Let's try to anticipate it. What's x squared plus 3? This is shifting the parent function x squared, which is the parabola, 3 units upward, right? So we're gonna get a graph like this, right? This is the tip, which is 3, the vertex, which is 3. Okay, so let's see which one it is. It's part C, so this is graph C, right? So let's write this down. So graph C. Okay, all right, let's do another one. Let's do one of these from 9 to 18, or actually a couple. How about we do number 12? Number 12 is, you have three functions, f, g, and h, and you would like to form this function, h times g. This function is going to act at 4. Okay, so what are the ingredients that are needed in 12? Just h and g, right? H and g, so just the last two. So I'm going to copy the last two. So this is on the same page, and that's number 12. We have h of x to be 1 over x minus 3, and g of x to be the absolute value of x plus 4, right? The question is, we need to find h times g acting at 4. So we need to find the output under the function a times g if the input is 4. Okay. Alright, so how does the product of two functions operate? How is this defined? Well, it's right there. It's just simply the product of the respective outputs. So this is equal, by definition, that we just visited in a second, this is equal to h at 4 times g at 4, right? So we're gonna find what 4 takes as an output if you input it in h, and we're gonna also find the output of 4 under the function g and then multiply the results. Okay, so h of 4, what's h of 4? The input is 4, so the x is 4. I'm gonna have 1 divided by 4 minus 3. Okay, so this value is h of 4 times g of 4, and g of 4 is the absolute value of 4 plus 4, correct? So h of 4 is simply h evaluated at 4, which means 1 divided by 4 minus 3, and g of 4 is simply g evaluated at 4, which means instead of x you're going to have 4, which is absolute value of 4 plus 4. And what's the result here? The result is, how much is this? 4 minus 3 is 1. 1 divided by 1 is 1, times the absolute value of the sum of 4 and 4, which is 8. Absolute value of 8 is 8. 8 times 1 is 8. Okay? So the image of 4 under the product function h and g is equal to 8. Okay? Alright, so now back to the book. Let's do another one. So we did 12. How about now we do 16. Let's do 16. 16 is, so you have f, which is negative 2x, and you have h. Those are the two ingredients, and you want to form the quotient of h and f evaluated at 7. Okay, so this is number 16. Let me write what h and f are. So h of x is 1 over x minus 3, and f of x is equal to negative 2x, and what we want to find is h divided by f, this quotient function, evaluated at 7. Okay, alright, and by definition, from the definition above, we know that this quotient function operates at a number as the quotient of the respective outputs. So h of 7 divided by f of 7, right? This is from the definition above. This is how this function is defined. Okay, so now the question is, what's h of 7 and what's f of 7? Let's find each one. How about we color each one? How about we color the top one by brown and the bottom one by blue? Okay, so let's find the top one, which is the red part or the brown part or orange. That's 1 over, right? H of 7 is 1 over 7 minus 3. Correct? One more time. H of 7 is 1 over 7 minus 3 because x is 7 this time. Okay? Alright. And f of 7, that's the blue output. F of 7 is negative 2 times 7, right? And negative 2 times 7 is negative 14. So negative 14. Okay. And let's now go back to purple. And how much is this? This is 1 divided by 7 minus 3 is 4, right? So 1 divided by 4, and the whole thing is divided by negative 14. Okay? Alright. If you see the answer immediately, great. If not, let's keep going. That minus, I can push it at the level of the fraction bar, right? I can get minus outside, 1 over 4 divided by 14. Correct? Let's keep this minus by itself. So minus 1 over 4 divided by 14. I'm rewriting what this fraction bar means. It means division, right? So 1 over 4 divided by 14. Now, how do you divide by a number? If you divide by a number, that's the same thing as multiplying by the reciprocal of the number, right? So we get negative 1 over 4, which is this guy. I'm gonna now write multiplication here, because I know division and multiplication are intertwined. Dividing by a number is the same as multiplying by the reciprocal of the number, right? Multiplicative inverse. And what's the multiplicative inverse of 14? Is 1 over 14. Correct? Alright, now how do you multiply two quotients? Straight across. You multiply the numerator and you divide by the product of the denominator, correct? So it's going to be minus the quotient. 1 times 1 is 1. And 4 times 14 is 56. Okay? So this is the output, minus 1 over 56. That's the image of 7 under the quotient function h over f. Okay? Alright, so let's go back to the book. How about 18? How about 18? H over g evaluated at negative 4. So h over g. So this is 18. What's h of x again? H of x is 1 over x minus 3. And g of x is absolute value of x plus 4. Okay. The question is find h divided by g evaluated at negative 4, if this makes sense. Let's see. So again, by definition, this is what? By definition, this is h of negative 4 divided by g, right? Of that negative 4. Okay? And what's h of negative 4? What's h of negative 4? It's 1 divided by negative 4 minus 3. Correct? Divided by g of negative 4. And g of negative 4 is the absolute value of negative 4 plus 4. Correct? And you're going to quickly realize that this guy here is 0. And upstairs is not 0, right? So this guy here is 0. And can you divide by 0? No, you cannot, right? So as such, this is going to be an undefined entity. And this means that negative 4 was not part of the domain of h and g. Correct? Was not part of the domain of h over g. So this is undefined. So technically I should have not written this part. So how about we color it in a different thing. So I'm gonna color it in pink. Just to let you know that this is something I should have not written, because I mean, you cannot write something you cannot write an entity divide by 0, right? This is nonsense. So I'm gonna put it in quotation here. You're not supposed to write it again because you're dividing by 0 and this is not meaningful. So this guy is undefined, and the reason it's undefined is because negative 4 is not in the domain of h over g. Remember what the domain of h over g is? What was it? The domain of h over g, the domain of a quotient function. This quotient function accepts input. Those inputs, where do they live? They live in the intersection of the domain of f and g, and they also have to verify that the guy downstairs, right, the guy downstairs evaluated at this number x should not be 0. So over here, such an x which was negative 4 gave me a 0 downstairs, and hence negative 4 is not in the domain of h over g. Okay? So since negative 4 is not in the domain of f over g, let's call it this way, d sub f over g is the domain, oh sorry, not not f, it's h over g in this case, right? So negative 4 is not in the domain of this quotient function d h over g. Okay, because negative 4 jammed the function h over g. Okay. All right. How about now 22? Let's do 22. The question is, refer to the functions r, p, and q, these functions. Find the indicated function, which is this product this time, and write the domain in interval notation. Okay? So 22. So we have the function r of x is equal to negative 3x, and we have that q of x is equal to square root of 1 minus x. And the question is, find r times q and give its domain using interval notation. You don't have to do it in interval notation, but let's do it in interval notation just for the sake of the video. So r times q acting at x, right? To understand how this function operates, I have to plug in something in it. And let's see the recipe of the output. By definition, this product function operates as the product of the respective outputs. So r of x times q of x, right? So these numbers get multiplied. That's going to be the output of this function. Okay, so r of x, how much is r of x? Negative 3x times how much is q of x? A square root of 1 minus x. Okay, so this would be the recipe of the output of this function. So this function here, r times q acting at x, outputs this guy. Okay, so this is how this function operates. All right, now what's the domain? What's the domain of r times q? What's the domain of r times q? Well, based on the very first page, the domain of r times q, so the domain of the product function, because it's the product of these respective outputs, then each one of them, as we discussed before, each one of them should be well defined, and this forces x to be in the domain of f and x to be in the domain of g, and hence x should be in the domain of the intersection, right? So the domain of the product is the intersection of the respective domains. So the domain of r times q is the domain of r intersected with the domain of q, right? Correct? Again, I'm adopting the notation d sub the name of the function is the domain of that function, right? Like here, d sub h over g is the domain of h over g. D sub r over r times q is the domain of r times q, the function, the product function. D sub r is the domain of r. D sub q is the domain of domain of q. Okay, so d sub r, what's the domain of r? Let's write it in a different letter, a different color. Domain of r, what is it? What's the domain of r? What's the domain of r? Well, this is negative 3x. So what r does, it multiplies the input by negative 3. Whatever, is there any input that doesn't produce an output given this recipe? Is there a number that you cannot multiply it by negative 3? Any number can be multiplied by negative 3, right? Because negative 3 times the number means you add this number 3 times by itself, and then you multiply it by negative 1. And this process can always be done, right? No matter what x is. So the domain of the function r is everything, all real numbers, right? Which is minus infinity to plus infinity. How about the domain of q? How about the domain of q? Let's write it here. Domain of q. What is it? Well, this function is a square root function, and we know that we've talked about it in earlier videos that such a function, the square root of a number, doesn't make sense except if this radicand is at least 0, right? So this guy should be 0 or more, because square root doesn't act on negative numbers. The least this radicand can go is 0, right? Okay. And what does it mean for this guy to be non-negative? What does it mean for this guy to be non-negative? When does this stay at or above 0? For which x? For which x? This means x should be less than or equal to less than or equal to 1, right? Correct? So 1 minus x is non-negative as long as x is at most 1. So this means the domain of Q is all real numbers that are less than or equal to 1, which means minus infinity all the way to 1, including 1. Make sense? Okay. So let's delete this part. Alright, back to here now. Now I know what each one is. D sub r is boldface r, the set of all real numbers, right? Which means everything. And intersect it with d sub q. D sub q is minus infinity 1, right? So one more time, I found what each piece is. D sub r, which was written in green here, and this is boldface r, so all real numbers, correct? And d sub q, which was written here in pink, is minus infinity all the way to 1, including that one. And now what am I doing? I'm taking the intersection between both of these sets. And what's the intersection between both sets? So you want all elements that are here and here at the same time. Well, any number here, it's already a real number. So the intersection becomes the smaller set, right? Minus infinity all the way to 1. This is the domain of the product function. Okay? All right. All right, back to the book. So we did 22. How about now we do 23, maybe? Let's do 23, even though it's odd, but probably it would be the hardest one among the rest. Let's do 23. Q over P acting at X. So 23. I need Q and P, so let me copy each one of them. Q of X is square root of 1 minus X. And P of X is given to be X squared plus 3X. Okay? And the question is, find Q over P acting at X, this quotient function acting at X. Okay, so, well, the definition of this, the previous definition says, this is simply Q of X divided by P of X. That's how this function operates. Okay, let me take the fraction bar at the level of the equality, just to keep it meaningful here, the writing. And this is equal to Q of X. Q of X is the square root of 1 minus X divided by P of X, and P of X is X squared plus 3X. Okay, so this would be the recipe of the output of the function P over Q. Q over P, right? Q over P. Okay. All right. Now the question is, what's the domain of this quotient function Q over P? Domain of Q over P. Okay. What's the domain of Q over P? We discussed it above. this is the collection of all numbers, right, that makes the numerator meaningful, the denominator meaningful, and the denominator not 0, right? So the x should make the numerator meaningful, which means x should be in the domain of Q. X also should make P of x meaningful, so x should be in the domain of P, and x should make P of x not 0, correct? So these are the three conditions. So these are discussed or were discussed over here, right, in this one. So the domain of a quotient function, you can only input those guys which are in the domain of F for the guy upstairs to be meaningful, and in the domain of G, so that the guy downstairs is meaningful, and the guy downstairs should not be 0, right? Okay. So this is then the collection of all guys that are in the domain of Q, right, and in the domain of P, with the property that P of x is not 0, correct? So these are the three conditions that are written as 2 here. These are the three conditions so that the output through the function Q over P is meaningful, right? Q of x should make sense. That's taken care of here. P of x should make sense, and this means that x is in the domain of P. And P of x should not be 0, right? It's right there. Okay. Alright, so let's unravel what this means now. What's D of Q? So what's the domain of Q? We found it above, right? D sub Q, we found it to be minus infinity all the way to 1, right? This is what we found above. Let's actually keep it in the same color, so which was pink. Okay, so this is pink and this is pink. These are the same thing. Okay, and what's dp? What's the domain of p? Well, this is what p is. P of x is x squared plus 3x. So what's dp? The domain is, the domain of p is what? So whatever x is, you're gonna square it, which means you're gonna multiply it by itself, and this doesn't place any constraint on x, right? So this is a number as long as x is a number. So you get this result, no constraints on x. Now this condition, this expression, does it require any special x? 3 times x, which means x plus itself 3 times, right? You can always add a number 3 times to itself 3 times. So this is also meaningful no matter what x is, right? So each of the two expressions is meaningful no matter what x is. So this whole thing then is, this whole thing which is p of x, this whole expression is meaningful no matter what x is, as long as it's a real number. So the domain of this function is all real numbers. Okay, so I'm gonna replace dp by boldface r, which is the domain, which is the set of all real numbers. That's the domain of p. Okay, such that p of x is not 0. And what is p of x? That's the expression p of x, x squared plus 3x. It should not be 0, right? Okay, so what did I do in the second step? I unraveled what this means, right? I wrote what each one represents in my current context. dq, domain of q, domain of this function was discussed above, right? Was here. So it's minus infinity all the way to 1. Right? I replaced dq by minus infinity all the way to 1. I need to intersect this, which means I'm going to take common elements with this guy, this set. What's dp? We discussed it. The domain of p happens to be all real numbers. Okay, so this function p accepts all real numbers. So the intersection of the two sets, I'm gonna take numbers x that belong to the intersection of both sets. In addition, I want to throw away among these guys that live in the intersection, I'm going to throw away those guys which make this expression x squared plus 3x, the denominator, 0. Okay, I'm going to throw them away. So how about we actually solve this equation? When does this equal 0? Let's try to understand what kind of demands I should place on x so that this expression is not 0. X squared plus 3x is not 0. You can factor out an x, right? You can factor out an x and you get x plus 3 for this expression, and you don't want it to be 0. And what does this mean? X times x plus 3 is not 0. When is a product not 0? If none of its factor is 0, right? So x should not be 0, and x plus 3 should not be 0. That's the only time a product is 0, right? A product is 0 if and only if both of its factors are not 0. Make sense? So x should not be 0 and x plus 3 should not be 0. And what does it mean for x? This means that x is not 0 and x should not be negative 3. Okay, I just added negative 3 to both sides here. So this requirement is the same as this requirement. Make sense? So those two are the same. Okay? So asking this is the same as asking this. So you can take this guy out and replace it by this. Let's do it. So this is then the set, the domain. I'm still after the domain. The set consisting of all numbers that are here and here. But any number that's a real number, right? Any real number is already, any number here is already a real number, which means the intersection between the two is simply the pink one. So x should be an element between that's smaller than or equal to 1. Correct? My point is, if you're trying to find the intersection between these two, the intersection between those two guys, okay, just a second here, right? If you're trying to find the intersection between this and this, you want elements that are here and here at the same time. Well, if a number is here, it's already a real number, right? So you can eliminate this without losing information. There is some redundancy, that's what I'm saying. Okay, so x should live here such that this should happen, and we unravel what this means in terms of x. It means that x should neither be 0 nor negative 3. Correct? So, long story short, domain of the quotient function is the collection of all numbers that are at most 1, this is what this is saying, with the property that they're not 0 nor negative 3. Okay? So what does this mean at the end of the day? What's this collection? What's this collection? How about we graph it on a number line? Try to understand what the constituents of this set are. Okay? So let's call the good ones green points and the bad ones red points. So where are the green ones? So all numbers that are from minus infinity to 1, including 1, if this is 1. So let me actually move it a little bit to the right. If this is 1, so all these numbers are good, right? All these numbers are good in terms of this condition. Now, throw away the 0, throw away the minus 3. So 0 is somewhere here. 0 is bad. And negative 3, which is somewhere here, is also bad. And the remaining ones are the green ones, okay, which are the good ones. Can we write these in interval notation? Can we write these green elements in interval notation? Well, this should be the union of 3 parts, right? This part here, this part, those guys, and those guys, correct? Including the 1. Who are these guys? What's the set representing those elements? These are minus infinity all the way to minus 3, excluding minus 3, because minus 3 is a bad guy. How about those guys here? Those guys are everything, all numbers between minus 3 and 0, right? Excluding the endpoints. And how about those guys? Those guys are from 0 to 1, including 1, excluding 0. Okay? So what's the collection of all the good guys? Each of this set of those sets, this guy, and this guy, are good points, contains good point. Now the collection of the union, right? The union of these three sets make up the set of all the good points. So this is then equal to an interval notation. Again, I'm respecting the question. The question is an interval notation. On a test, you don't have to write it in interval notation. You can write it in any way you want. You can say it in plain English as well. So it's minus infinity, minus 3, right? This is this part. Union, minus 3 to 0. Union, 0, 1. Okay? So alternatively, you can write it using set theoretic difference, if you remember that from our notation in this class. Using set theoretic difference, you can write it as all those guys which were minus infinity to 1, right? Throwing away the set containing these bad points, minus 3 comma 0. Okay, so you can use it, you can represent it using set theoretic minus, or you can just have interval notation, or any other way you want, as long as it's correct. Okay, so this is the domain of this function q over p. Okay, so the domain of this function q over p happen to be the collection of all numbers that are from minus infinity to 1, right, including 1, excluding minus 3 and 0. All right, let's continue. So we finished 23. How about now 30? So refer to functions s, t, and v, given as such, and find the indicated function and write the domain interval notation. So same question, now they kind of like cranked up the level of difficulty a little more. Let's do number 30. S minus t acting at x, where s is this quotient and t is this quotient. Let's do it. So number 30, s of x is equal to the quotient x minus 2 divided by x squared minus 9. And t of x is equal to the quotient x minus 3 divided by 2 minus x. And the question is, find s minus t, the difference function between s and t, acting at x. Okay? And by definition, this is simply s of x minus t of x. That's how the difference of s and t operates, right? S of x minus t of x. And s of x is this quotient, x minus 2 divided by x squared minus 9, minus t of x, which is this guy, x minus 3 divided by 2 minus x. Okay? Okay, so this is the difference function. This is the recipe of the output. Now, you're gonna say, probably one of the questions is, should we combine? Should we find the same denominator and so on? Yeah, you can, but the question consists of just finding the recipe of the difference, and this is the recipe of it. The other one would be an equivalent recipe, right? But it's not. We're not asked to do so. So I'm gonna just leave it like this. It remains to find the domain of that difference function, right? The domain of s minus t. And the domain of the difference function, because the output of the difference function is made up of the difference of the respective outputs, so I need each one to make sense, which means x should be in the domain of S and in the domain of T, right? So it's the domain of the difference is the intersection of the domain of those functions that are involved in this difference, correct? Again, this was discussed on the very first page of this section. It's right there. We're talking about the difference, and you can input in this difference function elements that are in the intersection of the domains, right? So that's exactly what I'm saying here. That's exactly what I'm saying over here. So the domain of the difference function is the intersection of the domains of the respective functions. All right, and what's the domain of S here? Let me just shift everything down to write explicitly what the domain of S is. What's the domain of S? The domain of this function. Well, this is a quotient. The domain of a function that outputs quotient is the collection of all points which make the numerator meaningful, the denominator meaningful, and the denominator not equal 0. The numerator is meaningful all the time. The denominator is meaningful all the time. And the only thing that I need to throw away is what makes the denominator 0, right? What makes the denominator 0. So when is x squared minus 9 equals 0? When does this happen? This happens precisely when x squared is equal to 9, and this is something we dealt with many times before. This means when x is plus or minus the square root of 9, which is 3. Correct? So these are the two guys that make this expression 0. And I need to throw them away. You don't want this expression to be 0, so you want to throw away those guys, 3 and minus 3. So it becomes all real numbers except those two guys, minus 3 and plus 3, right? I used set theoretic minus. Okay. All right. So this is technically an explanation for actually to find the domain, right? So this is an explanation here that was needed to actually find that domain. And how about the domain of T? What's the domain of T? The output of the function T is still a quotient, and a quotient is meaningful as long as the numerator is meaningful, denominator is meaningful, and denominator is not 0. Well, the numerator is meaningful all the time, because you can always chip away 3 units from a real number. The denominator, for a similar reason, the denominator is also meaningful all the time. So the only thing I need to throw away from all real numbers is the numbers that make 2 minus x equals 0. When is 2 minus x equals 0? Because that's the denominator. That guy is 0 if and only if x is equal to 2. Right? So the domain is all real numbers are welcome except the guy 2 and the domain T of the function T. Okay? So now we know what each one is. This guy was the green guy, and this guy was the orange or red guy, or whatever, brown. Okay? So the intersection of these two sets, which is the domain of the difference, should be consisting of all the elements that are in the green set and in the orange set, right? So who are in the green? All numbers that are neither minus 3 nor plus 3. So any number that's not minus 3 and that's not 3 is in this guy, in the domain of S. Who's in the red guy, in the orange set, the domain of the function T? Everybody except 2. Correct? So who's in the intersection then? Who belongs to the intersection? Who belongs to both of them? To the green set and to the brown set? Those are all real numbers that are neither minus 3 nor plus 3 nor 2, right? So this is the collection of all real numbers. Let me write it using set theoretic difference again. All real numbers except those guys, minus 3, plus 3, and 2. Correct? Those are the guys. Everybody except those three entities belong to this and this at the same time. Using interval notation, this is equal to, how about we do it here? So that's the number line, say. All real numbers are welcome except -3, 3, and 2. So -3 is somewhere here, that's a bad one. 3 is somewhere here, that's a bad one. And 2 is maybe here, right? So these are the bad ones. Everybody else is good. So all these guys are good. All these guys are good, right? Similarly here, all these ones are good. And these guys are good. Who are these guys? That's -infinity all the way to -3. Correct? So this would be the set consisting of all those guys. How about those guys? These are -3 to 2. How about those? These are 2 to 3, right? Again, all the endpoints are thrown away. How about these guys? These are 3 to plus infinity. Now you wanna adjoin all the green guys together to make up a set. So you're gonna adjoin all these sets. You're gonna take the union of these green sets. -infinity to -3. Union -3 to 2. Union 2, 3. Union 3 plus infinity. Correct? So we get this as a domain written in interval notation. You may also write it using set theoretic minus, or you can write it in using your own words. You may ask again the question, should I write 2 before 3 here? And don't forget, if you are listing the elements within a set, you can you can permute the elements, you can shuffle them around. As long as you list the element there, the order doesn't matter. Okay? So the order here doesn't matter because I'm listing the elements. Saying -3, 3, and 2 are there in the set, or -3, 2, and 3 are there is the same thing. Okay? Alright, so that would be the domain of this difference function that we just got here, right? Okay. Next. So we finished 30. How about 32 now? 32, you only need V and S. You need V and S. Okay? So let's do that. 32. You have V of X is equal to square root of X plus 3. And S of X is equal to X minus 2 divided by X squared minus 9. Okay? And the question is, find V over S acting at X together with its domain using interval notation. Okay? What's the definition of a quotient function? It's the quotient between those outputs, Vx and Sx, right? In this case. Okay, and what's Vx? Vx is simply square root of X plus 3. And S of X is this guy, X minus 2 divided by X squared minus 9. Okay? Let's be very, very clear. Who's the numerator here? Who's the numerator in this quotient? You have, it looks like I have 3 guys here. Who's what? Who's the numerator? The numerator is this guy, right? That's the numerator. And who's the denominator? It's S of X. So the entire thing here is the denominator, right? Okay. Now, what does division mean? It means you're dividing the numerator, which we agreed on is X, square root of X plus 3. You're dividing it by this denominator, which happens to be a quotient 2. X minus 2 over X2 minus 9, right? Correct? So one more time. I'm translating what this fraction bar is. It's division, right? Okay, between numerator and denominator. Very good. Now, division means multiplying by the reciprocal of the thing, right? So instead of writing division, I'm gonna write multiplication by the reciprocal of this guy. And what's the reciprocal of this guy? It's x squared minus 9 divided by x minus 2, right? Remember, reciprocal means multiplicative inverse. Multiplicative inverse is the guy so that you multiply it by this entity, you get a 1. And that guy would be this. You take the multiplicative inverse, which means numerator becomes denominator and denominator becomes numerator, right? So now we're going to multiply these entities. Remember, this means this is divided by 1. We're going to multiply these entities. And how do you multiply two quotients? You take the quotient of the product of the numerators divided by the product of the denominators, right? So upstairs you get the product of the numerators, so x squared minus 9 times the square root of x plus 3 divided by x minus 2, right? Over 1, so 1 times x minus 2 is x minus 2. Okay, so this is v over s acting at x. This is the recipe of the output under this function v over s. Now we need to find the domain of v over s, right? And we discussed this a couple of times above. Domain of the quotient function v over s. This is the collection, right, of numbers that live in the domain of v and in the domain of s, right? It should be in the domain of v and the domain of s, because you need the numerator to make sense of the output, the numerator to make sense, the denominator to make sense, and with the property that the denominator should not be 0, and the denominator is s of x, correct? So the domain of the quotient function is the collection of all elements that live in the intersection of the domains, as long as those guys do not make the denominator 0, correct? So we need to find dv, domain of v. We need to find domain of s. Let's do it. Let's make some room for this. And let's do it over here. What's the domain of v? What's the domain of v? Well, the nature of the output of v is a square root, right? And a square root makes sense as long as the radicand is non-negative. So you need x plus 3 to be greater than or equal to 0, which means x is at least -3, right? So all those guys are going to be part of the domain of v. So collectively they are -3 all the way to plus infinity, correct? So any number that's at least -3 is going to output, is going to make the v of x well defined. For s, what's the domain of s? We discussed it above, right? It's right there in green. So it's everything except -3 and 3. So since it was in green, I'm gonna keep it in green. So let's keep it in green. So this is then equal to all real numbers except -3 and 3, right? Let me change the color of this so that we don't confuse them. How about this is in pink now? Okay. All right. So the domain of v is all real numbers that are from -3 onward, and the domain of s is all real numbers that are not -3 nor 3. What's the intersection of the two? Actually, let me copy it before. So x is in, so this is the set consisting of all real numbers that are in the domain of v, and we color this brown. Okay, so let's keep it brown, which was minus 3 to plus infinity. Intersect it with the domain of S, and we colored this green. And what are those guys? Those are all real numbers except minus 3 and 3. Correct? You agree with this? Such that S of x should not be 0. And what's S of x? What's S of x? Is this quotient, x minus 2 over x2 minus 9. So x minus 2 over x squared minus 9 should not be 0. Okay? Alright. Now, what does this mean now? This guy. Well, this means it's the collection of all numbers that are from minus 3 onward, excluding, because I need the intersection, so and that are real numbers that are not minus 3 and 3. So putting things together here, this means x is a real number from minus 3 onward that's not minus 3 nor 3, right? So how would you write this then? How would you write this? This means the collection of all real numbers that are, you don't want minus 3, so that are bigger than minus 3, right? That are bigger than minus 3 and not equal to 3. So minus 3 to 3, union 3 to plus infinity. Am I correct on this? Let me try to illustrate this via a graph, a number line. So if this is the number line, I'm trying to understand who these guys are. Okay? So who are these guys? Well, any number from minus 3 onward is good just for this part. So from minus 3 onward is good. Minus 3. Everything is good. This is just the brown part. Now you wanna also retain points that are real numbers, but all these guys are real numbers that are neither minus 3 nor 3. So you're gonna throw away among these minus 3 and 3. So minus 3 now is bad. You wanna throw it away, and 3 is bad, right? So you're retaining only those guys which are between minus 3 and 3. It's right there. And 3 to plus infinity, which is that. So at the end of the day, you can say writing this thing, right? And writing this thing is the same. They are the same. Make sense? Just by illustrating what this means in terms of picture. Okay. Alright, so let's erase that. Such that x minus 2 over x squared minus 9, x minus 2 over x squared minus 9 should not be 0. Okay? Alright, so how about now we understand when this happens? When does the quotient x minus 2 over x squared minus 9 equals 0? So I want to understand when this quotient actually matches 0. Okay? So don't forget what we're doing. We're finding the domain of the quotient function v over s. We're down to this. It's the collection of all numbers that are from minus 3 to plus infinity, excluding minus 3 and 3, right? And among these, I want to retain those guys which make this expression not equal 0. So what I'm gonna try to find is, I wanna try to find where this quotient is 0 and throw away those guys from these and from this set, right? Okay. So when does this equal 0? When does actually a quotient equal 0? A quotient, a over b, when does it equal 0? When does a quotient equal 0? Well, a quotient is equal to 0 if and only if the numerator is 0, right? That's the only time a quotient is 0. Agree with me? You can think about it. If you want to go from left to right, you can multiply both sides by b. Correct? The understanding is that b is not 0 in this context because this quotient should make sense. b cannot be 0 for sure. So multiply both sides by b, you get a over b times b, which is a, is equal to 0 times b, which is 0. So a equals 0 if you want to go from left to right. Now if you want to go from right to left, you can divide by b, right? You can divide both sides by b and you get this. So these are equivalent statements, correct? Because of that, I can say this quotient is equal to 0. That's gonna play the role of my a, and that's gonna play the role of my b. The only time this quotient is 0 is when a is 0. That's what we discussed, and a is x minus 2, right? And a is x minus 2. So that's equivalent to saying when does x minus 2 equal 0? Correct? So these are the same question, right? So these are the same questions. Let me just make it this way. So this question and this question are the same. So when does x minus 2 equal 0? Because of this property, asking this blue question and asking this other blue question, it's the same thing. They're asking, we're trying to find the same guys. Okay, so when does x minus 2 equal 0? This happens when x is equal to 2, right? This happens precisely when x is equal to 2. Correct? Since this question is equivalent to that, this also happens precisely when x is equal to 2. Okay. So I know now what this means. This means that x should not be 2, right? I was looking for when this is equal to 0. Since you don't want this to happen, so you don't want x to be 2. Correct? Okay, so this was just a little explanation here on the side. Let's make it smaller and just keep it here. So this discussion is a tool to transition from this stage to the next, right? And the next stage is, let me make it a little longer than this. The next stage is actually this. Equal the collection, the set, I'm still talking about the same thing, of all numbers that are from minus 3 all the way to infinity, excluding minus 3 and 3, so which means this set, such that, right, such that this happens, but we understand when this happens, when x is not 2, right? When x is not 2. Make sense? So this part can be replaced by this guy. Again, I'm unraveling what it means in terms of x, because I need information. I need to find the domain of the function, and the domain is the collection of all the accepted input through the function, which is the quotient function here. So, and who's the input is x. It's denoted by x. So I'm trying to understand under what condition on x, v over s acting at x, right? V over s acting at x is meaningful. So far, the information I have is any x from minus 3 to plus infinity, excluding minus 3, excluding 3, and also 2, right? This is the last part, is a good guy for the function v over s. Correct? So this means, again, if you want to bring that picture again, the number line, all real numbers from minus 3 to infinity are good except minus 3 and 3. And now I want to throw away the 2 because 2 is there, right? 2 is among these guys. Throw it away and retain all the remaining ones. Those guys would be the good inputs for the function v over s. So who remains in the set then? Everything from minus 3 onward except minus 3, 3, and 2. So minus 3 to 2, union 2 to 3, union 3 to plus infinity, right? So why? Because on the number line, everybody from minus 3 to infinity, this set here, everything from minus 3 to infinity is good, right? Except minus 3 and 3. So minus 3 is bad and 3 is bad. And all the rest, I'm talking just about this part, all the rest were good at the time, right? All the rest were good. Now, in addition to this discussion, in addition to this, I need to throw away the 2, right? Among these, among all the green guys, I'm gonna throw away the 2. So let's throw it away. And where does 2 happen? It happens somewhere here, right? And how do you interpret the remaining ones using interval notation? Those guys are those guys are those, and those guys are those. The union of all three makes up the green portions of the axis that you see in the picture. Make sense? Alright, so this is then the domain of the quotient. Okay. Alright, we're gonna go now to the book and select more problems. Still on the same page, page 225. Let's do problems here from 33 to 36. We're given a function in each instance, and we need to find, for part A, we need to find f of x plus h, and for part B, we need to find f of x plus h minus f of x over h. Let me first explain the geometrical meaning of this quotient. Okay, this quotient is very important. You're gonna see it, for those of you who are going in calculus, you're gonna see it a lot in calculus, and it's actually a foundation there. Okay, so let's explain what this quotient means. So let's suppose we have if an xy plane, and we have a function there. Okay, so let's take the function to be, say, f. Okay, and let x be a point in the domain of the function f, and let's add to x an entity h. If h is positive, then we're gonna move to the right, correct? So let's say x plus h is here. H is positive in this context, right? H is positive. If h is negative, x plus h becomes on the other side, right? Okay. So you have x here, x plus h here, and in this context, a is supposed to be positive. What is then this height? What's this height? Well, this is f of x, right? This is f of x. Okay. How about this height? This is f of x plus h, correct? F of x plus h. The input is x plus h. So the output is this height. Am I correct? So we have this point and this point. Let's call this point A, and let's call this point B. Okay. So what are the coordinates of A and B? The coordinates of A are x comma f of x, because it belongs to the graph of the function, so it should be a guy, f of the guy, right? And what are the coordinates of B? They are this guy, x plus h, comma f of that guy, which is f of x plus h, correct? Okay. Now, let's take the line that crosses through the point A and B. So let's take the line that goes through the 2 points A and B. This is called the secant line joining A and B, right? So this is called the secant line joining A and B. Okay. All right, what's the slope of this line? What's the slope of this line? Remember the slope formula? So the slope of the secant line in the picture is given by what? Change in y over change in x, correct? Change in y over change in x. What's the change in y here? What's the change in y? That's the change in y. This guy, right? This is the change in y. Agree with me? Which is the same as this guy. Which is the same as this guy. And what is this? This is f of x plus h. This is this guy minus this guy, right? F of x plus h minus f of x. This is the change in y. How about the change in x? How about the change in x? That's the change in x. Agree with me? Which is the same as this. And how much is the change here? We said we increased it by h, right? This is the difference between x plus h and x is simply h. So this distance is h, right? So this would be the change in x. So you get this quotient, which is the slope of the secant line joining a and b. And this quotient actually is called, it has a name. This quotient is called the difference quotient. Okay, so the difference quotient. Okay, so it's a quotient of differences, change in y over change in x. So long story short, this quotient is simply, which has a name, difference quotient. It's simply the slope of the secant line joining the point whose coordinates are x comma f of x and the point whose coordinates are x plus h comma f of x plus h, right? So this is the average rate of change between the points a and b. So the average rate of change between the points a and b. Let me also write that down. So that is to say, the average rate of change between the points A and B. Okay, which means, how much over this interval of time, which is of length h, how much was there change in y, right? This is what the average rate of change between the 2 points mean. Okay. All right. So this is very useful. You're gonna see this a lot, especially at the beginning of calculus. Back to the question here. This question is purely algebraic, so we are given a function and we need to find f of x plus h, and then we need to find the difference quotient pertaining to that function f. Let's do, how about 36? F of x is x squared minus 3x. So 36, f of x is x squared minus 3x. And for part A, we said we need to find f of x plus h, right? So they need to find f of x plus h, which means this height. This height here, right? This height. Okay. Well, f of x plus h, remember how we do this? Forget about the name x. How about star? F of star is the square of the star minus 3 times the star, right? Who's my star now? That's my star, x plus h. So what do we get? We get the square of that star, which is the square of x plus h, minus 3 times the star, and the star is x plus h. Agree with this? Okay. Now if you want to expand this, what's the square of x plus h? It's x plus h times x plus h, right? You FOIL it out. We did it before. You get x squared. We did it in an earlier video, not in this video. So x plus h squared is x squared plus twice the product of x and h plus the square of h, right? If you don't trust me on this, you can FOIL it out. X plus h times x plus h, put them back to back and FOIL it out. Minus 3x minus 3h, right? Correct? So we expanded it. This is f of x plus h. Alright, so now allow me to just erase these things that help me find this. Now the question in part B is find the difference quotient, which is the quotient between the numerator, which is f of x plus h minus f of x divided by h. Okay? Alright, f of x plus h, I just found it. It's all this guy. So x squared plus 2xh plus h squared minus 3x minus 3h. Correct? This is this guy minus f of x, and f of x is x squared minus 3x. Agree with me? Let's be very clear again. F of x plus h, let's color it in brown. It's this guy, right? And f of x, let's color it, oops, sorry, my bad. So this should remain brown. Now f of x, let's color it in blue, and that's this guy, divided by h. Divided by h. Okay? And obviously they want us to simplify this if possible. So let's try. So I have this over h still. Upstairs I have, let's destroy the parentheses here. Those parentheses are not doing anything, right? So I'm gonna destroy them. X squared plus 2xh plus h squared minus 3x minus 3h. That's the orange or the brown part. Minus, let's destroy these parentheses. I'm gonna bring in the minus. Everybody inside is gonna switch sign. So I'm gonna have minus x squared plus 3x. Correct? Okay, now I'm gonna simplify like terms. Minus x squared plus x squared gone. Minus 3x plus 3x, they're gone. Okay, so let's color it differently. These are together, and I'm left with everything else. So what am I left with? So I'm left with, I still have the h downstairs, 2xh plus h squared, right, minus 3h. These are the survivors upstairs. Okay, so we have this then. So we have this. Can we simplify by anything here? I realize that h is a common factor upstairs. Let's factor it out, right? So let's factor out h upstairs. We get 2x plus h minus 3, correct? If you factor out an h, you get 2x plus h minus 3, and the whole thing is divided by h. Okay, and now can we simplify? Can we simplify by h, which is a common factor between the numerator and the denominator? Yes. Okay, because I have a multiplication, it's a common factor. H is a common factor, so h divided by h is 1, and you are left with 2x plus h minus 3. Okay, so this would be the difference quotient of this function f of x, which is x squared minus 3x, which is that much. Okay. Let's do one more problem pertaining to difference quotient. Let's do 44. The question is find the difference quotient and simplify, which is, and the function involved now is 1 over x plus 2. Okay, so this is 44. The function is f of x is equal to 1 over x plus 2. And we want to find the difference quotient, which is the slope of the secant line, right, between the 2 points just discussed above. F of x plus h minus f of x, so change in y, over change in x, which is h. Correct? Okay, so I need to find each of the guys, f of x plus h and f of x. F of x, I know it. What's f of x plus h? So let's call this star to not to confuse the x's and so on. What's f of x plus h is if f of anything is equal to 1 over the thing plus 2 is gonna be equal to 1 over my star here happens to be x plus h, so I get x plus h plus 2, right? So that's x plus h, that's the star guy, plus 2, correct? Minus the f of x, which is the star now is x, so 1 over x plus 2, and the whole thing is divided by h, correct? Let me just erase this fraction bar, it's annoying. I'm gonna just keep it at the level of equality. Okay, so we have this, and then what? And then what? We're gonna simplify. This is what they want us to do. We need to simplify this ugly looking quotient. Okay, let's try our best. This is equal to, dividing by h is the same thing as 1 over h, right? Times that numerator, which is 1 over x plus h plus 2. This is this guy, minus 1 over x plus 2. Correct? This is not a necessary step. I'm just writing it this way just to work on that numerator, this one, just separately, okay, in a clean way. Alright, so what I'm gonna do is I'm gonna make the same denominator between those guys. So how about the product of their denominators being that common denominator? Okay, so I'm gonna keep this guy like this. I'm gonna write each one of them as the product of these denominator, which is x plus h plus 2 times x plus 2. Okay, so I'm multiplying downstairs by x plus 2, right? I'm multiplying downstairs by x plus 2. So I gotta also multiply upstairs by x plus 2. And 1 times x plus 2 is x plus 2. Okay, so what am I saying here? I'm saying I'm rewriting this as something over the product of the denominators, which is x plus h plus 2 times x plus 2, while maintaining the value of the quotient, right? Look, if you simplify back these green guys, they are the same guys. So we're back to this. So we didn't change the value of the quotient, but we changed the format. Okay? Minus, still the same game I'm gonna play here. We had x plus 2 before. How about we multiply now by x plus h plus 2 to have that common denominator, right? So I'm multiplying by this guy. And since we multiply downstairs, we gotta also multiply upstairs by this guy, which is x plus h plus 2, because I had 1 above, right? 1 upstairs. So 1 times x plus h plus 2 is x plus h plus 2. And one more time, divide those two red guy or orange guys, you get back this thing, which shows that the value of the two quotients are the same, but the format is different. But this format is suitable for us to actually combine the two quotients, because now I have a common denominator, and now we know how to subtract two fractions which have the same denominator, correct? So how do you subtract two quotients which have the same denominator? You glue them together in some sense, right? So you have that common denominator, which is x plus h plus 2 times x plus 2. And upstairs we have the green part, which is x plus 2 minus, right, minus the brown part, which is x plus h plus 2. Correct? And I hope you realize that these brackets are not necessary because I have multiplication here. This is a multiplication, right? Okay, so I glue them together, I get x plus 2 minus that guy, the whole thing. This is wrong. If you erase the parentheses is wrong, because you're gonna subtract the entire numerator, right? The package, the numerator, and you divide by this common denominator. Okay. All right, and then what do we get? We get 1 over h times the quotient, whose denominator is x plus h plus 2 times x plus 2. And upstairs we have x plus 2 minus, let's destroy the parentheses, which means everybody inside switching sign, x minus h minus 2. Okay? Let's now simplify. X minus x, 0. 2 minus 2, 0. So the only thing that survives upstairs is simply negative h. Correct? So we have 1 over h, that's this guy, times negative h, that's the survivor upstairs, divided by the product of x plus h plus 2 times x plus 2. Okay? And how much is this? Can we simplify any further? Negative h divided by h, you're only left with negative 1, right? So we get negative 1 upstairs divided by, here I have 1. 1 times this is that. So x plus h plus 2 times x plus 2. Okay? This is a multiplication here. And this is the difference quotient pertaining to this function in 44. F of x is 1 over x plus 2, right? Okay. We're going to next consider a new way on how to combine functions. So we've studied 4 operations between functions, 4 new ways on how to combine functions, namely adding, taking the difference, and multiplying, and taking the quotient. So these are new operations we defined between functions. Now we're gonna consider a new way on how to combine functions, and that new way is illustrated by this diagram over here. We're gonna think about a function as being a machine. Let's suppose we have 2 functions, the pink function and the purple function. The pink function is named g, and the purple function is named f. So we're gonna create a new function out of these 2. Let's color it in this, in red. This is the big machine, right? This is the big machine, the red box, that's made up of 2 components, the g function and the f machine, and they operate as follows. Or the big box, the big machine operates as follows. You send in an x in this big red machine. It goes first to the g machine. So g is gonna operate on this x, the input, and it's gonna output something. So it's gonna output g of x, right? It's gonna output g of x, and that output is gonna turn into an input in the function f. So f is gonna now act on this guy, and when f acts on something, we're gonna the output is gonna be f of the thing, right? And the thing here is g of x. So the output is gonna become f of g of x. So f of g of x. Okay? And that output, that guy, is gonna be the output of the entire machine, the big red machine. Okay? So one more time. The red machine, the red box, operates as follows. You send in an x in it. That x hits g first. G is gonna operate on it. It's gonna produce an output, and we call the output g of the input, right? G of x. So that's the output. Now, that in turn is going to turn into an input in the function f, the purple one. And when f operates on the input, the output is going to be f of the input, right? And the input is g of x. So f of g of x, so f of g of x, that's going to be the output. And that output, we're going to consider to be the output of the big red machine. Okay? So we are composing those two functions, g and f, in this order. G acts first, and then it spits out an output, and that output turns into an input in f. And once f finishes operating on that input, it's going to produce an output, which is going to be the output of the entire machine. Okay? So what's this entire machine, the red machine? It's a composition of two functions, g and f, where g acts first and f acts second. And the notation of this red machine is f circle g. So f circle g is a function that operates as follows. You send in an x in this composite function, f circle g. It hits g first. It hits the one that sits on the right first. And then g is going to output g of that input. So if the input is x, it's going to output g of x. That's going to become an intermediate output, which in turn is going to become an input in the function, now the left function f. And then when f operates on this input, is going to produce an output, which is going to be the output of the entire function, f circle g. So that output is going to be defined to be, so that output is going to be defined to be the output of the circle machine, right? Of the composite function. So f circle g acting at x. Okay? So f circle g acting at x, that's the recipe of the output. X goes to g first, and then you're going to produce g of x, and then g of x is going to go to f, and then the output is going to become the output of the entire machine. Okay? So keep in mind, it's written f circle g, but g acts first. Okay? It operates in a reversed fashion. Okay? So the idea is that x goes here, and then the result goes in f. Okay? Alright, so the formal definition reads as follows. Given two functions f and g, so we're given those functions, the composite function f circle g, which is also called the composition of f and g, is defined by the following. This function, f composed with g, acting at x, is equal to, by definition, it equals to the output of this process. So f acting at the input g of x. Okay? Alright, let's go to the book and consider a few problems. That's on page 226. And let's do, how about 52? So we have a function f, which is given as x cubed minus 4x, and we are given a function h, which is 2x plus 3. The question is, evaluate the function for the given value of x. In this case, minus 1. Okay, so let's copy that. So this is 52. So page 226, number 52. What do we have? We have the function f of x equals x cubed minus 4x, and we have the function h of x equals 2x plus 3. Okay, and they asked us to find f composed with h at the point -1. Right? This is what the question is. And how does a composite function, or how is it defined? at a point, if you evaluate it at a point, that's the same thing by definition. That's the definition, right? That's the definition. It's the same thing as the left one. The left one is acting at the output that the right one takes on the input. Okay, so long story short, in this case it's gonna be, again by definition, it's gonna be f acting at h of -1. Correct? So technically g is h in my context. Okay, so we get this. If you wanna keep track of it and based on the diagram, here we have h, we don't have g, right? Here we have h, so we're gonna plug in the number, what is it, -1. We're gonna plug in -1 for x, and that guy is gonna go in the composite function, is gonna hit h. H is gonna produce h of -1. We need to find it, that thing, because we have the recipe of h. And once we find h of -1, that number is gonna go as an input in the function f, and the output of the function f is gonna be the output of the composite function f composed with h, right, at -1, which is technically f of h of -1, right? F of this number, h of -1, whatever that h of -1 is. So this is pictorially, but you obviously we have to present it algebraically. So this is equal to f of h of -1. How about we highlight this in a different color? Okay, how about the green? So what's h of -1? Let's write the answer here. What's h of -1? Well, h of anything is twice the thing plus 3, right? What's h of -1? We need to plug in -1 here, right? So, and the input sits right there. 2 times -1 is -2, right? Plus 3. What's -2 plus 3? That's 1. So h of -1 is 1, right? So let me write the actually the explanation here. H of -1, that guy, as we discussed, it equals to twice -1 plus 3. I'm following the recipe of the output through h, and this is -2 plus 3, which is simply 1. Okay, so h of -1 is 1. So 1 is gonna sit right there. Okay, so back to the diagram, h of -1, which is the intermediate piece, that guy happens to be 1. Now this number 1 is gonna be sent as an input in the function f, and the output is gonna be f of that 1, right? So the output of the composite function is gonna be f of that number 1. Okay, and what is f of 1? Well, f of anything is the cube of the thing minus 4 times the thing. F of 1 is 1 cube, right? 1 cube minus 4 times 1. Okay, and what's this number? 1 cube, 1, minus 4 times 1 is 4, which is -3, right? So if you plug in the composite function f composed with h the number -1, you get out -3. Okay, all right, let's do more problems from this group. About 58. So we have g composed with f acting at -4, and f is as before, while g is square root of 2x. Okay, so that's number 58. Let's do it on the second page. So that's number 58. We need to evaluate g composed with f. So let's give ourselves what g is. G of x is equal to square root of 2x. And f of x was given as x cubed minus 4x. Correct? Okay. So in 58, the question is find g composed with f acting at -4. Okay, so same process. By definition, a composite function outputs the following. The composite function g composed with f acting at -4 is going to output the following. It's going to output g of f of -4, right? Correct? So -4 goes in the composite function. It goes to f first. That's right there. It goes to f first. F is going to produce an output. F is going to produce an output. That output is going to then go into G, right? G is going to wait. It's not going to do anything over here, right? And while this middle piece is manufactured, this guy here, which is the left function, is waiting. It's not doing anything. Once this is done, that goes as an input on the left in the left function. Okay? All right. So what do we have? -4 goes to f. F is going to operate on -4 and it's going to produce what? So that guy is equal to, that's the recipe of f, and the input is -4. So instead of x, we're going to have -4 in this case, right? And what's -4 cube? Let's write the whole thing. So -4 cube minus 4 times the blue 4 times that guy, -4. So -4, right? Okay. What's -4 cube? It's -64, right? -64. And minus 4 times itself is plus 16, which is -48. Correct? So that guy at the end happens to be -48. Then we're gonna send it as an input. That guy, -48. We're gonna send it as an input. Let's keep it in red. So let's keep it in red. We're gonna send this guy as an input in G. Now G is gonna operate on this number, and we know how G operates, right? It takes the square root of twice the input. So the square root of twice the input. Correct? Okay. So just think about it for a second. What do we have here? Square root of 2 times -48. Whatever this guy is, I'm not gonna compute it. 2 times -2 times, sorry. Whatever this guy is certainly negative, right? And square root of a negative number doesn't make sense. Correct? So since this is not meaningful, that number then is undefined. Right? Undefined. Correct? So technically all this guy should have not been written. Okay? Because the square root of a negative number doesn't make sense. So I'm gonna put here quotation just to let you know that everything here written is not meaningful, because at the end of the day we found something that's undefined. So that gives us a feeling also gives us it implies that -4 is not part of the domain of this composite function, correct? Because if it were in the domain, we're gonna get a defined answer, but in this case, or a defined output. In this case, it happens to be an undefined output. So -4 jams the composition because it jams the last piece, right? It jammed this one. This function here doesn't accept negative, correct? In this case, the function g, which is the square root function, it doesn't accept negative numbers, and I'm sending in -48, right? I'm sending in -48. So that's gonna jam g, and hence the process is jammed, and the process is not gonna produce an output. Okay. All right. Let's keep going. Look, this is for 62. You have composition of 3 functions, right? But the process of composing 3 is the same as composing 2 at a time. You can think about this as one function and then compose it with f. Actually, let's do it. So 62. 62. So we have, let's understand first how f composed with g composed with h is gonna output or is gonna operate on an input. Well, I can think about, let's say, how about this? I can think about it as one function, right? I can think about it as one function because this is one function, or this is a function. So I can think about that as one function. How about we label it something else? How about we label it w? So I'm gonna think about this guy as w. Okay, so what this means is that I can rewrite this as w composed with h, correct? At x. So w composed with h at x. I'm renaming this guy to be w. So this would be my definition of w, right? Okay. And then we know how we compose two functions. I'm trying to understand how to compose three functions. We know how to compose two functions. It's simply, by definition above, it's simply w, the left one, acting at the output of the right one, correct? So this is the definition. Okay, and now let's reveal what w is. W is the composition of f and g, correct? So w, I can replace it by what it means, and what it means is f composed with g. That's what w is, correct? Okay, and keep that guy h of x. So this function now, which was labeled as w, is gonna act on h of x. Okay, so this is a number, don't worry about it, it's a number, whatever it is. I'm gonna send it inside this composite function, correct? If you're bothered with the label h of x, how about star? F composed with g acting on something, how does it operate? Well, this is simply, by the definition above again, f at g of the star, right? This is how the composition of two functions is defined. The left one is gonna act on the output of the right one acting on this guy. Yes? So the left one is f, the right one is g, so f of g of star. Correct? Okay, and then what star? What star now? It's h of x. So let's replace this guy by h of x. Okay. So all in all, what do we have? The composition of three functions behaves exactly as you might guess. X goes to h, we get h of x, and then h of x is gonna go to g. H of x, right, is going inside g, and then the result is gonna go inside f. And what's the result? This whole thing becomes the result that's going as an input in f. Okay? So the behavior of composition of three is very much intuitive if we understand how 2 operates. Okay? And so on and so forth. If you have 4, etc. The output of 1, of the 1 to the right, is gonna go as an input in the 1 to the left, right? And that sequence is gonna keep going like this. Okay, so now we understand how composition of 3 function is defined. Let's go back now to the book and understand what we need to do. We need to evaluate f composed with h composed with g at 8, right? And f, g, and h are here. Okay, so let me take this 62 over here. Okay. Alright, so 62 is, we have f of x, which is x cubed minus 4x. We have g of x, which is the square root of 2x. And we have h of x, which is equal to 2x plus 3. Okay. Let me keep this writing in blue. Okay. All right, so the question is, find f composed with h composed with g at 8. Okay, so here the names of the function, it's not I mean, the order here is different than the one in 62. Okay, this is why I shifted the number 62. So we have technically the g in this discussion is the h here, and the h in this discussion is the g here. Okay, but anyway, we know how this thing operates. This is gonna operate based on the discussion above. So this is based on discussion above. So discussion above. Okay. This is gonna operate as follows. So f is the last one that's gonna act, and what's gonna act on is the output of h, right? And what h is gonna act on is what g output at 8. Okay, so 8 goes to g, we get g of 8. G of 8 is gonna go in h, so we get h of g of 8, and then that result is gonna go in f, and we get the output of the entire thing. All right, let's do it in steps. How about finding g of 8? What's g of 8? Well, g of anything is square root of twice the thing. This thing happens to be 8, so we get twice of 8, right? Twice 8. And twice 8 is 16, and that thing is 4, right? Square root of 16 is 4. So we have then f is still waiting. H now is gonna operate on this result, which is 4. Okay, so that guy now is done. It's 4. It's sent inside h. We get this. Now h is gonna operate on 4. F is still waiting. It's not doing anything. H now is gonna produce an output on 4. And what's that output? Let's find it. So h of 4 is how much? H of 4 is twice 4 plus 3, right? And twice 4 is 8. 8 plus 3 is 11. So this is 11 then. So that's 11. Correct? And now 11 is going to go as an input in f. And f is going to operate on it. It's going to produce 11 cubed, right? 11 cubed minus 4 times that guy 11. Correct? And here you get, the answer should be 1, 2, 8, 7. Don't worry about the answer, just as long as you understand how these things operate, that last step is not necessary. I can accept this as a final answer. Okay? All right. Let's do number 64 now. So we're given k of x to be minus 3x plus 1 and m of x to be 1 over x. In part A, we're asked to find k composed with m at x. So that's 64. We have k of x equals minus 3x plus 1 and m of x equals 1 over x. Okay? The question is, in part A, find k composed with m at the point x. Okay. So the definition of composite function is as follows. The left one is gonna act on the result that the right one is gonna act on the input, right? The result of the right one acting on the input. So we get this. So k is gonna wait for m of x to be manufactured, and m of x is 1 over x. Now the 1 over x is going inside k, right? The 1 over x is gonna go inside k. Too many x's, how about labeling it something else? How about star? K of star is minus 3 star plus 1. Who's my star now? That's my star, right? The star is 1 over x. So what do we obtain? We get minus 3 times 1 over x, minus 3 times star, which is 1 over x, plus the 1. Okay? And this is simply minus 3 over x plus 1. Okay? The minus 3 times 1 over x is minus 3 over x plus 1. So we get this. So k composed with m at a point x, that's the output of this function. Okay? So let's actually box it. So k composed with m at x produces this output. Okay? Alright. Now the second part, part B. What's part B? Part B, find m composed with k now, the other way, the other order. So find m composed with b. Part B, we want to go for m composed with k at x. Okay? So again, the same thing. The left one is going to wait for the output to be produced by the right one. So m of k of x, which is equal to m of k of x. What's the output through k if the input is x? Well, it's minus 3x plus 1. Correct? Minus 3x plus 1. That guy k of x is minus 3 of x plus 1. Minus 3x plus 1. Okay? And then m is gonna operate on this. And what does m do? It takes the reciprocal of that thing. Whatever that thing is, it takes the reciprocal of it. And who's the thing here? Who's the input? Minus 3x plus 1. So what m does is gonna take the reciprocal of minus 3x plus 1. Correct? So this would be the result. This would be the output of the composite function m composed with k. Okay? Here I forgot to write the by definition this is happening. Okay. The last part, which is C, is k composed with m and m composed with k the same? Are they the same? So if you plug in an x in k composed with m and you plug in an x in m composed with k, do you get the same thing? So technically what I'm saying is the output via k composed with m, which is this, and the output via m composed with k, which is this, right? Are they the same? They don't look the same, but this is not enough. We have to find an x where where both of them exist and they're not the same. Okay? So how about finding x to be how about 3? How about 3? So k composed with m at 3 is equal, right? K composed with m. I'm replacing x by 3. What do we get? Minus 3 over 3 plus 1. Correct? Don't forget, what am I doing? I'm trying to show, the question, are they the same, right? If you reverse the order of the composition, do you get the same answer? Apparently we don't. The two outputs are different. They don't look the same, and I'm making the case. To make the case that they're not the same, it suffices to find an x where this expression is different than this expression for the same x. Correct? I'm choosing the x to be 3. If you take x to be 3, this becomes minus 3 over 3 plus 1. And what's minus 3 over 3? Is minus 1, right? Plus 1, which is 0. Okay? Whereas the other one, m composed with k at 3, which is this guy at 3, I'm still talking about the same x, right? Is equal to 1 divided by minus 3 times 3, the x is 3, plus 1. Correct? And what is this? This is 1 divided by negative 9 plus 1. And negative 9 plus 1 is negative 8. So you get minus 1 over 8. Correct? Doesn't matter what the answer is. But for sure, this is not 0. Correct? And that's different than 0. That's different than 0. They're different. Correct? So since those two are different, then for the same input, these two functions produce different entities, which makes the case that the order matters. When you compose functions, the order matters. It's different than when you add functions. When you add functions, the order doesn't matter. F plus g is the same as g plus f, for obvious reason. But if you compose, you may get different functions, as this example illustrates. Okay, so as a consequence, the operation of function composition is not commutative, right? So as a consequence, the operation of function composition is not commutative. Okay? Which means if you compose functions, you may not get the order may matter, so it does matter when you compose functions. You may get different functions depending on the order. Okay, sure. Sometimes if you compose functions, sometimes you get the same function, but the idea is it's not a universal thing. So in general, you should not expect them to be the same. Okay. All right. Let's now move on to the next example. Let's go to page 227 and let's do a problem from 91 to 98. The question is, find two functions f and g such that h of x is equal to the composite function between f and g acting at x. So they gave us h. We need to decompose h in two functions. Okay, we need to decompose it in two functions so that if you recompose them, you get back h. Okay, let's go to how about we do 94 and 98. Okay, let's do 94. So we're given that h of x is the fourth root of 9x minus 9, and we are asked to find two functions so that if we compose them, we get back h. Okay, so let's go to page 227. That's page 227, and that's number, what is it, 894, right? So you have h of x equals the fourth root of 9x minus 5. And the idea is we need to find f and g so that if we compose them, we get back h, right? So if you compose those two in this order, f composed with g, so g is going to act first, followed by f. That function is going to be the same thing as the function h, meaning if you plug in an x over here in this function and you plug in an x over here, they're going to match. Okay, this is when two functions equal each other. They equal each other provided for the same input you get the same output, right? Okay. So there is no one way to do it. There are many functions that do this job. Let's choose the most obvious ones, or the most intuitive, f and g. How about thinking about x or thinking about g as the function that produces this 9x minus 5. So you plug in an x, it goes to g, right? And then g is gonna produce this. When g produces this, that's gonna go to f. So it's worth thinking about f as being the fourth root function, correct? It's like the outer function being the f and the inner function being the g, right? So let's try this. Let's try these choices. So consider or introduce, as we said, the function f of x to be the fourth root, the outer one, the fourth root of an input, and we label the input to be x. If you're not comfortable with x, forget it. How about bullet? Okay. So let's introduce this function. It's the fourth root function, and the function g of x, which is gonna go inside f to produce this. That's being the function f. So this better be the input in the function f to produce the same result as h. So 9x minus 5. Okay. And again, if you're not comfortable with the choice of x, go for bullet. Okay. All right. So what's g of x is 9 times x minus 5. And what's f of x is the fourth root of the x. So in words, f of the input is the fourth root of the input, and g of the input is 9 times the input minus 5. Now let's check, let's verify that this is actually the case. So let's verify that our choices of f and g actually answer the question. So let's verify now that the composition of those two functions matches h. Okay, so if you compose them, you get h. So let's verify this. Okay, so what's f composed with g acting at x? We're gonna send an x in this function. The way it's gonna operate, again, by the definition of composition of functions, it's gonna be f acting at g of x. Now g of x, so f is waiting, is not doing anything. G of x is, g of anything is 9 times the thing minus 5. So g of x is gonna be 9x minus 5. And now this 9x minus 5 is gonna go as an input in f. And what f does to an input, it takes the fourth root of that input. And who's the input now? Is 9x minus 5. So 9x minus 5 is gonna go in f, and f is gonna produce the fourth root of that input, which is 9x minus 5. And isn't that the same as h of x? Isn't that the same as h of x? So what can you say then? What can you say then? No matter what x you plug in f composed with g, as long as it's in its domain, and we'll talk about domain of composite functions shortly. So no matter what x you send in the composite function, it's gonna be the same as that x sent to h, right? The outputs are identical. So what can you say then? Since the outputs are identical for any given input, then those two functions must be identical, right? So that makes the case. That's the verification part. Okay? All right, so as I promised you, we're gonna do the 98. H of x now is 11 over x minus 3. So this is 98. So h of x now is given to us as 11 over x minus 3. And the question is the same. Find f and g such that f composed with g is equal to h, right? That's the question. Okay. So how about, take a moment, obviously, to think about it for yourself and try to come up with those functions. For me, what I'm going to do is I'm going to think about g, which is the one that's going to operate first on an input. I can think about it as being that guy. Okay? So g of x, I can take it to be x minus 3. And then f of an input, I'm going to take it to be 11 over whatever the input is. Okay? So I can think about this guy here as g of x, and then the 11 over that an input, the 11 over the input is the f function. I can think about it this way. Again, there are many functions that do this job. Okay, don't think about my choices as the choices. There are many ones. Okay, I'll explain this when I finish the current choice. So let's do it. So let's consider f of x to be, as I said, the 11 over the input, the 11 over x. Again, if you don't like the input to be x, how about bullet? So 11 over the bullet, and g of x, or g of an input, bullet, is equal to the bullet minus 3. I'm thinking about this as being the output through the function g if the input is x. So g of bullet is bullet minus 3. That's how I'm gonna think about g. With this choice of f and g, I'm gonna verify, so I'm gonna check that my choices are appropriate. So let's check that the composition of f and g in this order is equal to that function h that was given. So if I recompose them, if I compose f and g, I get back h. So I'm going to send an x in f composed with g in this function. I'm going to send an x there. And I'm going to show that I get back the same thing if I send an x to h, meaning I'm going to get this. Alright, so composite function, how does it work? Again, by definition, it's f of g of x. So it's the left one acting on the resultant output when the input x goes to the right one. And then g of x in this context is the input minus 3, so x minus 3, right? G of x is x minus 3. And f of anything is 11 over the thing, right? F of something is 11 over the thing. Well, I'm talking about f of x minus 3. So x minus 3 is my bullet here, right? That's the thing I was alluding to here. So I get 11 over that guy, x minus 3, right? That's how the function operates. Okay? And isn't that h of x? Isn't that h of x? Yes, it is. And then, since this happens no matter what x is, so no matter what x you send in the composite function f composed with g, and you send it to h, the outputs are the same. Therefore, you may infer that my choices are correct, and as such, the composite function f composed with g is equal to h. Okay? Let me make now the point that there are more than these choices. These are not the only choices that you may that you can have. There are infinitely many. Okay? Let me illustrate this point. So this would be an alternative choices. So alternative way. So alternative way. Again, this is to illustrate the fact that I may have infinitely many choices of f and g, so that if I compose them, I get h. Okay? Alright, so look, what I'm gonna do is, for instance, what if we consider So what if we let f of x to be, and you're gonna see why. Okay, you're gonna see why once I choose them. Keep in mind that these are the most obvious ones. Okay, these are the obvious ones. This is a little bit more intricate, but still it should be obvious after we do it. So 11 divided by, how about I go for x plus 1. Okay, so how about I go for this? Meaning, so what f is gonna do is, f of anything is gonna be 11 over the thing plus 1, right? This is how this new function f operates. And what I'm gonna do for g, is I'm gonna take it to act on an input x as x minus 4. Okay, again, if you don't like the choice of x as being the input, choose the bullet. Okay, so f of anything is 11 over the thing plus 1, and g of anything is the thing minus 4. These are my choices in this alternative approach, or alternative way. And let me make the case now that these choices actually also verify this equality, this identity, f composed with g is equal to h. So let's also verify now. So verify that for these choices of f and g now, we still have this. Let's verify that. Okay. Let's send in an x in the composite function f composed with g. And this is by definition, this is equal to f of g of x, as usual. This is how a composite function operates. And this is f of g of the input, and the input is x here, so g of x is x minus 4. Correct? And finally, we're gonna take a look at how f operates. Well, f of anything is 11 over the thing plus 1. And my thing happens here to be this guy, right? X minus 4. So f of the thing is 11, f of x plus minus 4 is 11 over x minus 4 plus 1, right? So it's 11 over the input, which is x minus 4 plus the 1. Agree with me? So we get this. And now, what's downstairs? X minus 4 plus 1. Isn't it x minus 3? Minus 4 plus 1, isn't it minus 3? So x minus 3. And 11 over x minus 3, take a look. 11 over x minus 3, wasn't it h of x? That's h of x. Correct? And that makes my point. So I sent in an x in this composite function, and I sent in the same x to the function h, and what did I get? I get that they are the same thing. So what can you infer? That f composed with g is equal to h, as I claimed earlier, right? So you get the point now. You should get the point at this juncture. Meaning, you can, for example, here have any number you want instead of 4, and any number you want instead of 1. And what you want at the end of the day is that negative this number plus this number to actually equal negative 3. Correct? For example, you can go here for 2 and here for 5, right? And so on and so forth. So I hope I made the point that since you can go for any numbers you want as long as their sum, so minus this number plus this number should be minus 3, you have infinitely many choices. Okay? And this makes my earlier point that you have infinitely many choices for functions f and g, for example in this problem, to actually so that once you compose them you get back h. Okay? Alright, let's now go to another type of problems. Still on the same page, let's do 102. Okay, let's do 102. I'm not gonna do all of it. I'm gonna just do you know what? Okay, I'll do all of it. So let me take it as a picture. Let me just take the whole thing as a picture, paste it here. So this is problem 102 on the same page, which was 227, right? Okay. So I want to find, in each instance, I want to find the value of the given function. Let's talk about the first one, part A. Let's talk about the first one, part A. I'm given m plus p, the function, the sum function between m and p, acting at 1. Okay? And based on the definition of the sum function, this is the same as m of 1 plus p of 1. This is how the sum function operates, right? Okay? And what's m of 1? We need to look at the picture. Which function is the m? It's the blue one, right? It's the blue one that's the m. So m of 1. What's the value that m takes when the input is 1? What is 1? This is input 1. And what's the value of the blue function, which is the m function, when the input is 1? It's this height, right? This is m of 1. This is m of 1, this height. This is the point whose coordinates are 1 comma m of 1, right? Agree with me? And how much is this height? That's 4, right? This is equal to 4. Okay? Alright. Now, let me just clean this part. Now, we still have to do the same work for p of 1 this time. For p of 1. So what's p of 1? The function p now is the pink function, correct? The p function. P of 1, that's the 1 again. P of 1 is this guy. That's the height p of 1. Yes? That's the point whose coordinates are 1 comma p of 1. And what's that y coordinate? It's a 2. It's a 2. So that's a 2. Okay? Alright. And this means that m of 1 plus p of 1 is 4 plus 2, which is 6. Okay? So the function, the sum function, m plus p is gonna take the value 6 when the input is 1. Correct? That's how you interpret this. Meaning, if you try to graph the function m plus p, which is the sum of the two functions, it's gonna have an output 6 at 1, right? So the function is gonna be maybe somewhere here. This is where the function m plus p is. Okay? Remember, m plus p is just the sum of the two. So point by point, I'm gonna just add. At each point, I'm gonna add the two outputs, right? So for example, here at 2, I'm gonna add this plus this, which is 1 plus 3. So it's gonna be 4. The function, the sum function is gonna be there, right? And so on and so forth. So it's gonna be point by point, and then whenever you add them up, you're gonna have the function m plus p. Okay? Alright. Next, part B. P minus m acting at -4. So part B, let me change the color. At part B, P minus m acting at -4. Okay? And how does the difference function operate at a point? You just take the difference of the respective outputs. So p of -4 minus m of -4, right? And we're gonna do the same thing. So I wanna find p of -4. So I'm gonna go to the p function, which is the pink one, and I'm gonna go for input -4, and input -4 is right there, right? So that's p of -4. That's p of -4. And how much is that? That's 4, right? That's 4. Okay. And now I need to go and find m of -4, and the function m this time, the blue one. M of -4, that's -4 again. M of -4 is this depth, right? And how much is this depth? That's -2. Correct? Alright, and now you just subtract the results. So you subtract the -2 from the 4, which means that's a 6. Correct? Okay, part C. M over P at 3. So part C, M over P, the quotient function, acting at 3. And based on the definition of quotient function, I know that this is gonna equal, again by definition, M of 3 divided by P of 3, right? Okay, and what is M of 3? What is M of 3? This is 3. M of 3 is this height. Correct? M of 3 is this height. That's the point whose coordinates are 3 comma M of 3. And how much is that? How much is the y value? It's a 2, right? That's a 2. So upstairs is 2. So this guy happens to be 2. And how about the other one? The guy downstairs, which is P of 3. P of 3. The P function. P of 3 is... This is where 3 is, and P actually is on the x-axis. This is an x-intercept. So this point has coordinate 3 P of 3, and P of 3 is clearly 0 in this case, right? This guy is 0. Because the function is on the ground. The y value is 0. Okay? So that guy then is 0. So this guy is 0 downstairs. And this is 2 over 0. What is it? This is an undefined entity, correct? So it's undefined. Undefined. Correct? So technically, again, I should not write that this guy 2 over 0. The writing is not meaningful. I'm gonna put quotation here just to let you know that I got the undefined by trying to evaluate it, but I was led to find an entity which is not defined. 2 over 0 is not a defined answer. It's not a defined number, so not a defined expression. So this becomes an undefined answer. So M over P is not defined at 3. So 3 is not part of the domain of M over P, right? Okay. Fourth part, which is the D. The D, we need M times P at 3. So M times P, this is times, not the composition, times P at 3. Okay. Okay, and based on the definition of how you multiply functions, that's M of 3 times P of 3. Correct? And what's M of 3? We just found it above. That's a 2. That's a 2. Correct? We just found it above. And what's P of 3? Also we found it above. That's a 0. So it becomes 2 times 0, which is simply 0. Okay? So M times P, the value it takes at input 3 is actually 0. Okay, part E, M composed with P acting at 0. So part E, M composed with P acting at 0. The way composite function operates is the left one waits for the input of the right one at that input, right? In this case, 0. Okay, and what's P of 0? What's P of 0 based on the function? So I'm gonna go to the function P and look what value it takes at 0. This is the function P. At 0, it takes this height. This is the point whose coordinates are 0, P of 0, right? And apparently the P of 0, which is the y value of this point, is a 2, right? So it's a 2. So this is a 2, and then we obtain m of 2. So now m is going to operate on the output of this function, which is a 2. And m of 2 is how much? So let's clean up the picture a little bit. M of 2. This is where 2 is, and this is the m function, so that's m of 2 then. Correct? This height is m of 2. And how much is this height? It's a 3. It's a 3, right? So that guy is 3. So m composed with p at 0 takes the output, takes the value 3. Okay. F, we need to find p composed with m at 0. Right? So it's the other way around. We're composing it backward. And we just talked about that I should not expect the same answer because the operation of function composition, which is the circle, is not commutative, right? So the order matters when you compose. Okay, so I should not expect the same answer. Let's try it. Based on the definition, my 0 looks like a composition. Let me just make it more oval. P composed with m at 0, this is the same as p now acting at the result that m is gonna produce at 0. And m of 0 is how much? Let's check this. M of 0. M of 0, this is 0. M of 0 is this height, right? Is this height. That's m of 0. And how much is it? That's a 4. Correct? That's a 4. So that's a 4. And then this becomes p acting at 4. And let's see what p outputs when the input is 4. So let's clean up. P acting at 4, right? This is the p function, the pink one, at 4. This is input 4. But the function p, which is the pink one, has a hole here, right? And nowhere else is defined. So 4 has no output through the function p. In other words, there is no point on the graph of p whose first coordinate is 4, right? There's no, I mean, on this graph, on the pink graph, there's no point whose first coordinate is 4. So as such a point is not defined on the graph of p, and therefore for input 4 the function p doesn't produce any output, meaning 4 is not part of the domain of the function p. Okay, alright, so this is an undefined entity, so p of 4 is undefined. Let's consider a hypothetical situation. What if instead we had, let's say, maybe I should stick to the same color. How about, let's suppose that the function p makes this dance, and at 4 it makes a jump from this piece of the graph all the way to here. Okay, so let's suppose that this guy is actually on the graph of p. As such, its coordinates are going to be 4 comma p of 4, right? And according to the graph, this guy now is how much? Negative 4. Okay? So in this hypothetical situation, the p of 4 would have been minus 4. Okay? But this is just a situation I created. This is not part of the problem. So let's erase it. Okay, so we're down to G, the last one. P at m of negative 4. So that's part G. So G. P acting at, so acting at m of negative 4, right? This is the same thing as saying P composed with m the composite function p composed with m at -4, right? So technically they give us this writing, which is the same as this writing if 0 is replaced by -4, based just on the definition, right? Okay. Let's do this. P of m of -4. How much is m of -4 is? Did we find it before? I think we found it above. Yeah, m of -4 happened to be -2. We did it before, right? That guy is -2. So this becomes P of -2, right? This guy is -2. P of -2. And we haven't found that. Let's do it. P of -2. Where is -2? It's right there. That's -2. What value this input takes through the function P, which is the pink one? It takes this height, right? How much is this height? It's 4. Yes? So that's a 4 then. Okay. So P composed with M at -4 is equal to 4. Let's now move to the last concept in this section, and let's ask the following question: what is the domain of a composite function f composed with g? So recall the diagram, right? The way, the graphical way how a composite function operates on this picture here. Let me actually copy that and try to now answer this question based on the diagram, because this is how a composite function operates pictorially, right? So let's go back to that page and paste it. So what's the domain of the composite function, right? That's the question. What's the domain of the composite function? Okay, let's see. So we send in an x. Remember domain, what it means? It means the collection of all the accepted inputs through this composite function, through this red box, the big box, right? So I want to look for those x's that allow the process to go smoothly and then the process or the function to produce an output, correct? So I want to see what type of conditions I have to place on the input x so that the whole thing goes smoothly, meaning the red function doesn't jam. The red function doesn't jam provided each of the two sub-functions doesn't jam, right? So let's see. So if x is sent inside the big box, the composite function, we know it goes first to g, right? It goes first to g. Now, for this guy to be produced, for the function g to produce an output, you need x to be accepted by g, correct? You need x to be accepted by g, because if x is not accepted by g, the process stops here, and then the composite function doesn't produce an output. So you need x to be accepted by g. And what does it mean for x to be accepted by g? It means that it should live in the domain of g, correct? So requirement number 1, so let me call it R1, meaning requirement 1. This is my first demand on x. X has to be in the domain of g, correct? Let's think about dg as being the domain of g. Alright, so this is number 1. So one more time. If x is sent inside the box, I'm looking for the process to go smoothly, meaning no jamming. So I want to place conditions on x so that the process goes smoothly and the output is produced. X goes inside the big machine f composed with g. It goes to g first. So g has to produce an output when x is sent to it. So this means x should be accepted by g, which means x should live in the domain of g, right? This is condition number 1. Okay, so now under this condition, this is produced, right? This guy is manufactured. Next, I'm gonna send this result, which I know under this condition, this result is gonna be defined. It's gonna be produced. Now I'm gonna send it inside f. So for the process to keep moving smoothly, I need this guy now to be accepted by f. Like I used to play before, the same game. I need now this guy, which is now the input in f. That guy, I want it to be accepted by f, correct? And what does it mean for that guy to be accepted by f? It means that it should live in the domain of f, right? So that's requirement number 2. You need this guy, which is g of x, to be accepted by f, which means it should live in the domain of f, correct? And then, if this guy is accepted by f, f is going to be able to output that thing, and which is going to be the output of the entire machine. So this is going to be okay now. It's going to be produced. And the process is smoothly gone as long as this demand is fulfilled and this one as well. So it's a combination of the two requirements. Okay? So what are the conditions on x so that x is accepted by the composite function and hence lives in the domain of the composite function? X should be, number 1, in the domain of g, right? And here, in the domain of this function. And then its output, which is g of x, should be in the domain of f. Okay? So these are the only two demands that guarantees the process to go smoothly. Let's combine these. Let's summarize this this discussion and our findings by writing out what the domain of a composite function is. So the domain of f composed with g is, so let's denote it by d sub f circle g. So the domain of this function, the composite function, is equal to, I'm gonna just put these two conditions, right? It's the collection of all numbers, let's call them x, that live in the domain of g, right? So this takes care of condition 1, such that among these I wanna only retain those which allow me to say that g of x is also in the domain of f, right? So I'm not gonna take all the x that live in the domain of g, because I have a second requirement. Among these, I'm gonna just take those which allow g of x to be in the domain of f. Okay? So this is what the domain of a composite function is. The composite function here being f composed with g. So the domain of f composed with g is equal to the collection of all the numbers that live in the domain of g, with the property that g of x should also be in the domain of f. Okay? So the domain of the composite function is actually a subset of the domain of the right function, because what lives here are guys in the domain of g, in the right one, right? But not all of you may lose some of them based on this condition, because not all of them may verify this condition. Okay, so among those, I'm gonna keep those which allow g of x to stay in the domain of f. Okay, so this is the reasoning, and this is the result. And now let's put it in action. Let's go to the book. Let's go to the book and let's go to page 226. This is page 226, right? It's right there. And let's do number 80. So the question is, find the composite function f composed with g and write the domain using interval notation. Okay? So let's take it as a snapshot. Paste it here. So this is still on page 226. And now I need to find the composite function along with its domain, right? How about we find the domain before we find the composite function? Let's find the domain of f composed with g, where f and g are given concretely now. We're not talking about abstract f and g. We know exactly what f is and what g is. Okay, based on the property above, how about we label it something? Let's call this property. How about we call it property, I don't know, musical note. Okay, let's call it the musical note property. So based on this property, the musical note property, I can say that this is equal to the collection, I'm just going to copy it, the collection of the point that live in the domain of the right one, G, so in this case is also G, with the property that G of X, so this guy G of X, is in the domain of F. Okay? I mean, here luckily we have the same label, but if this is labeled as W and this, let me change the color. If this is labeled as W and this is labeled as H, so you're gonna apply this, there's no F and G anymore, right? Think of, I mean, the G is the right one, so G would have been H and F would have been W, or the other way, W would have been F and H would have been G in this musical note property, right? Okay, so very good. So that's the property we just developed. I employed it, but now I can unravel what it means because I have a concrete recipe for F and a concrete recipe for G. Okay? So I need to find the G and I need to find the F. Let's find that. Let's take this down a little bit. Over here. Let's find, because I mean to unravel it I need to find the G and I need to find the F, right? So let's find that. What's the G and what's the F? How about the F first? What's the domain of F? The domain of F, you should be now familiar with how to find the domain of a quotient. You should be convinced that this is all real numbers except -4, right? The domain of this function is the collection of all real numbers except -4. How about the domain of G? How about the domain of G? The domain of G is the collection of all real numbers that allow the numerator to exist, but the numerator also is a constant, so it exists all the time, and the denominator to exist, but the denominator exists for all real numbers, and the last part is that I need the denominator, which is x squared minus 1, not to be 0, correct? And how or when does x squared minus 1 match 0? This happens precisely when x is plus or minus 1, right? If you don't want this to be 0, you don't need x to be 1 and you don't need x to be -1. Okay? So these are the two guys that I need to throw away from the domain of G. So the domain of G is all real numbers except the -1 and the 1. Agree with this? Let's erase this part. Okay, so now I have a full understanding of what the domain of F is and what the domain of G is. Let's take this knowledge now to unravel this set. So this is then equal to, I'm gonna keep going here, now I know what the G is. So this is then the set of, what does it mean for x to be in the domain of G? For x to be in the domain of G, it means that x is a real number that's neither -1 nor 1, right? That's what it takes for x to be in the G. Okay? So this means x, oops. So this means x is a real number such that x is not -1 and x is not 1. Do you agree with this? Let me color it so you know exactly what piece corresponds to what piece. This corresponds to this, right? Saying this or saying that is the same thing. Correct? Now, for this part, let's color it in blue. Oops. One more time. So let's color this part in blue. What does it mean for g of x to be in the domain of f? What does it mean for g of x to be in the domain of f? Well, for g of x to be in the domain of f, it means g of x is a real number that's not negative 4, right? That's what it takes for something to be in the domain of f. It should be a real number, but g of x is for sure a real number because I'm taking x to be a real number that's not negative 1 nor 1. This means g of x is gonna be an output, so it's gonna be a defined thing, and hence it's a real number. So certainly g of x is a real number, but now to be in the domain of f, it should not be negative 4, right? So g of x should not be negative 4. Agree with this? Do you agree with that again? Let's try it. So this light blue, which means x is in the domain of g, to be in the domain of g in this context, it means that x should be a real number that's neither negative 1 nor 1. So that's the light blue part, right? So it's a real number that's neither negative 1 nor 1. For that blue kind of blue color, g of x is in the domain of f, and the domain of f contains all real numbers that are not negative 4. So for g of x, for this guy to be in the domain of f, it's already a real number, so I need it not to be negative 4. Okay, so I'm down to this. And now let's ask the following question. What are the x that allow me to say that g of x is not negative 4? So what's the condition on x so that g of x is not negative 4? Because I need the domain of the composite function, right? So I need to find all the accepted inputs, and the input is denoted by x, right? In this discussion. So I need to know what this means for x. All right, what does it mean for x so that g of x is not negative 4? Well, g of x is 3 divided by x squared minus 1, right? This is what g of x is. G of x is 3 over x squared minus 1. So this thing then becomes the same thing as saying that 3 divided by x squared minus 1 is not negative 4. That's the same thing, because g of x is this expression, right? So if you don't want g of x to be negative 4, that's the same thing as saying that this expression, which represents g of x, to be different than negative 4. Okay, and let's solve this equation, meaning finding the x's that allows this expression not to be negative 4. Okay, so how would you solve this equation? You multiply through by x squared minus 1, so you get 3 is not equal to negative 4 times x squared minus 1. What did I do here? I multiplied both sides by x squared minus 1, right? Some people learn it as you cross multiply, same thing. Okay, so you get this. Okay, and what is that? This is the same thing as saying that 3 should not equal minus 4x squared plus 4, right? So one more time, I distributed the multiplication over subtraction. Minus 4 times x squared is minus 4x squared. Minus 4 times negative 1 is plus 4. Okay, I'm after x. Because I need to know what conditions on x I should place so that I accept it in the domain of the composite function. So let's keep unraveling this in terms of x. So this is the same thing. If you subtract both sides by 4, you get 3 minus 4 is negative 1 is not equal to negative 4x squared, correct? And this is the same thing as saying, by dividing both sides by negative 4, this is the same thing as saying that 1 over 4 is different than x squared, right? I swap the sides. I divide both sides by negative 4. You get 1 over 4 here, and you get x squared here. So x squared should not be 1/4. Okay? And what does this mean in terms of x? This means that x should not be plus and negative square root of 1/4. Right? So it should not be plus or minus square root of negative square root of 1/4. And what's square root of 1/4? It's 1/2, right? So x should be different than plus 1/2 and minus 1/2. Okay? So this analysis here written in brown is to unravel what this condition is, to unravel what type of demands I should place on x based on this blue condition right there. And the condition is that x should not be negative half and x should not be minus half. So this is what this is saying, is that x should not be negative half and should not be half. Okay, they're the same thing. All right, now we put things back together in this set. This set then is equal to the collection. I'm gonna copy. X is a real number such that x is not negative 1, x is not 1, and the condition that I discovered here, which is this, and x is not negative half, right? And x is not plus half. Correct? So that's what this is saying. Okay, so oops, let me just fix it. Anyway, don't worry about it. I mean, let's just move all these guys to the side so we make room for this and this one here. Okay. Anyway. All right. So, long story short, the domain of the composite function f composed with g after this analysis that we just made is the collection of all real numbers that are neither minus 1, nor 1, nor minus half, nor half. Okay? So this is the collection of all real numbers except those 4 guys. And they asked us to write it in interval notation. So if you think about the number line, everyone is invited to this set except those 4 guys. The largest or the smallest among these is minus 1. Second smallest is minus half. And then half. And then 1. Those are the bad guys, right? And everything in pink is good. So let's write it in interval notation. What are those guys? Those are minus infinity all the way to negative 1, excluding negative 1, union everyone between minus 1 and negative 1/2, excluding the endpoints, obviously. Right? All those guys now, which means negative half to 1/2. And then from 1/2 to 1, so I'm still gonna adjoin them. 1/2 to 1, and then from 1 to plus infinity. Correct? This is the set written in interval notation. If you prefer to write it using set theoretic minus, it's the set consisting of all real numbers except throwing away those 4 guys. So throwing away this quartet, minus 1, minus half, 1/2, and 1. Okay? Alright, so that's how we find the domain of composite function. Let me summarize the steps again. We started by this property that we discovered, right? And I unraveled it, meaning in this case I found what dg is and what df is. I replaced by what they mean, and this is gonna give me a condition in terms of x. You unravel it, you find that condition or those conditions on x, you put things together, and you get out you get the set that you want, which is the domain of the composite function. Okay. All right. So this is part 1 of the question. Part 2. We need to find the recipe of the function f composed with g at x, right? We need to find the recipe of f composed with g at x. Okay, so this is by definition f at g of x, correct? F at g of x, and that's the same thing as f of g of x, and g of x was given to us to be how much? G of x was given to us to be 3 over x squared minus 1. So 3 over x squared minus 1. Yes? Now, f is acting at this result. So f is acting at this result, which is 3 over x squared minus 1. And how does f operate? How does f operate? F of anything is equal to the thing over that thing plus 1, right? Who's my thing here? It's the g of x, so it's this guy, 3 over x squared minus 1. So that's the guy who's gonna take the role of my star, and hence it's gonna sit here and it's gonna sit here. Okay, so let's copy that. So this is then equal to the quotient of the star, so 3 over x squared minus 1 divided by the star minus 4, right? Plus 4. This is what the recipe is, and the star here is this guy. So I'm gonna have 3 divided by x squared minus 1. So one more time, this is the guy who's playing the role of my star. This is the structure of the output of f. F of star is star divided by star plus 4, right? And my star happens to be 3 over x squared minus 1. I'm gonna place it here and here. Okay, and then let's do some aesthetics here. So let's simplify the expression. What I'm gonna do is I'm gonna create a common denominator downstairs. If you create a common denominator downstairs, so we're keeping the guy upstairs, 3 over x squared minus 1. The guy downstairs is 3 over x squared minus 1 plus 4. This is how it is now, right? I'm gonna make the same denominator downstairs, so I'm gonna create an x squared minus 1 underneath 4, right? So I'm gonna create an x squared minus 1 underneath 4 so I can get the same denominator. And since I divided by this number, to preserve the value of this quotient to be 4, I need this entity here to remain 4. So I need to also multiply upstairs by x squared minus 1. Right? Realize that this remains a 4 if you simplify back. Okay? So then I'm gonna add those two because I have a common denominator at this point. Downstairs I'm talking. So I have a common denominator. 3 over x squared minus 1 upstairs is still untouched. Downstairs I have that common denominator x squared minus 1. And what's the numerator here? 3 plus this guy. So 3 plus 4 times x squared minus 1. Okay? Alright. Let's simplify this writing. This is equal to 3 over x squared minus 1. And I'm gonna simplify this guy. I'm gonna simplify it, and it's gonna be sitting under or over that x squared minus 1, right? Let's try to find the simplified version of this. What is this piece? This is 3 plus 4 times x squared. Let me erase the parentheses. So x alright, 3 plus 4x squared minus 4, right? And this is 4x squared minus 1, because minus 4 plus 3 is minus 1, right? So who sits here then? This is 4x squared minus 1. And I hope you start realizing some pattern we did before in the domain and finding the domain. We're talking about this technically here when over here minus x4 or plus x4 minus 1. We're talking about this guy, right? Okay. And we're down to this. But this can be simplified. This can be simplified. Let me ask you the following question. What's A divided by B? This is my numerator. And this guy is divided by C divided by the same B. That's the same B, okay? That's the same B. What is this? That's the same as, let's try to simplify it if possible. That's the same thing as A over B divided by C over B, right? That's what the fraction bar means. It means the division, correct? Okay. And dividing by C over B amounts to multiplying by the reciprocal. So it's multiplying by the reciprocal of C over B, which is B over C. Okay? And what is this? This is AB over BC, right? Which means that you can simplify by B and get A over C. And get A over C. Correct? So the structure that I have here is the same as this structure. And let me make it clear for you. This is my A. This is my C. Correct? This is my A and this is my C. And those guys is the same B. And this guy and this guy are the same B. Correct? So the structure is the same as this structure. A over B over A over B. The whole thing is divided by C over B. And according to our work here, this expression can be simplified as just the A over C. You can ignore the B. The B's are going to cancel eventually, right? As you saw over here. Right? So this discussion now is employed, let's say here, and to simplify. And what do we get? What do we get? Just a second, let me just clean up here a little more. Okay, so like this. So one more time, what do we get here? We get equal to A over C, right? A over C, and the A is 3 and the C is 4x squared minus 1. Makes sense? As we just found here, it's A over C at the end. So A, which is 3, and the C is 4x squared minus 1. So what is this? That's the recipe of the output of the composite function f composed with g if you plug in an x. And what's the domain of this function? What's the domain of this function? The domain of this function is the thing that we just found above. All real numbers except those 4 guys. Correct? Look, if you wanna find the domain of the composite function just based on its final recipe, you're gonna look. This final recipe is obscuring things. If you try to find the domain, if I give you just this recipe over here, if I just give you this recipe and I ask you to find the domain of this, you're gonna say, oh, the only guys that I should throw away are the guys that make the denominator 0. And the guy downstairs is 0 when x is plus or minus half. You can see it. So it looks like just the plus and minus half are the bad guys. But don't forget, in the process, we eliminated the x squared minus 1, right? It was part of the discussion. If x squared minus 1 was something that's not, if x squared minus 1 was something that's not defined, which means if x squared minus 1 is 0, then this process could have not been gone smoothly, right? If x squared minus 1 is 0, this guy doesn't exist. And as such, I could have not continued. So my point here is looking at the final recipe of the composite function and judging or creating or trying to understand what the domain just based on the final recipe may be misleading, because that final recipe may be an embellished version of the actual output of the composite function. This is the actual output of the composite function. This final recipe is just an embellished version of this, right? Assuming that this version exists, then you can simplify by x squared minus 1 in the process. Okay? So when you want to find the domain of a composite function, I strongly encourage you to go through this process that we just described above. It tells you exactly what you need to throw away and what you need to consider, because it takes in account all the conditions that you have to place on x. Remember the discussion we had here, R1, R2, the conditions, requirements 1 and 2. These two conditions are the only conditions for the whole process to go smoothly, and I would strongly encourage you to start from the musical note property that we just discovered. Okay? Alright, let's do another one. Let's do now, how about 82? So given g of x to be the square root of x minus 3, we need to find g composed with itself. So g composed with g, and write the domain interval notation. Let's do this. That's number 82. Okay. So we have g of x equals that, and we need to find this guy together with its domain. Let's start with the domain of g composed with g. Okay? Based on the musical note that we established above, right? Based on this property, what can I say? Let's visit that. I'm talking about this one, right? So who's my f in the current context? We need to find the domain of g composed with g, right? So the f is actually g. So what I'm gonna have is, it's gonna be the collection of all the numbers that live in the domain of this guy, which is g, such that the output through this function, g of x, is in the domain of f, but f now is g. Okay? So let's do that. This is gonna be the collection of, let me just keep it in purple, the collection of all numbers that live in the domain of g, with the property that the output through g should live in the domain of the left function, which is also g. Make sense? Okay. So, and now I know what g is, so I need to find its domain. So let's leave some room here for the domain of the function g. What's the domain of g? Well, the function g outputs the square root of the input minus 3. And I know that the square root function doesn't operate on negative entities, right? So in order for this output to be meaningful, I need to put conditions on x, and this condition actually is that this x minus 3, the guy that sits under the umbrella, is non-negative. And what does it mean for x so that this happens? This means by adding 3 to both sides that x is at least 3, right? Agree with this? So the domain of g then is all real numbers except all real numbers that are from 3 onward. So 3 onward. Okay, so that's what dg is. All right, Down, back to this. Back to this. I can replace, I know what dg is now at this point. It's only numbers that are from 3 onward. So this means, again, let's keep it as before. Let's keep, color code this this discussion. So what's in brown here is gonna now be written in brown. This means that x is in the domain of dg, which is this. So 3 plus infinity, correct? Such that let's now have this guy in a different color. How about blue? So what does this mean? dg, I know what it is, and g of x, that's g of x, right? G of x is the square root of x minus 3. So I can replace g of x by square root of x minus 3. And for this guy to be in the domain of g, right? What does it take for something to be in the domain of g? It should exist, but I know by now that this guy is gonna exist because x is in the domain of g. So this guy exists, and also it has to be bigger than or equal to 3, right? So this means that it should be bigger than or equal to 3. One more time. The blue part, g of x is in the domain of g. G of x is square root of x minus 3. That's what g of x is. And for something to be in the domain of g, if something exists to be in the domain of g, it should be a number that's at least 3, right? So this guy, this number should be at least 3. Make sense? Okay. And now we need to find what this means in terms of x. We need to find what this means in terms of x. Well, both of these guys are bigger than or equal to 0, right? Both of these guys are bigger than or equal to 0. And if I square both sides, let me just illustrate what I'm saying just using a graph. Remember the parabola? It's a bad one, but remember the function y equals x squared, which is the parabola like this. So if you give me a number, a and a number b, and they're both positive on this side of the x-axis, what's a squared in terms of b? This would be a squared. Oops. This would be a squared, right? And this would be b squared. Do you agree with this? So if a is smaller than b, then a squared is going to be smaller than b squared, correct? Keep in mind that a and b both should be on the right side of 0. Okay? But on the other side of 0, let's switch colors. Let's switch colors here. So how about green? On the other side of 0, if you give me a and b as in the green part, what's a squared in terms of b squared? This is a squared now. And this is b squared, right? Let's say. Who's bigger? Now a squared is bigger than b squared, correct? So if a and b, if a is still smaller than b, but now on the left side of 0, then what you get is the other way around. A squared is bigger than b squared. And the reason, as you might guess, is that the function here is decreasing, right? So what used to be smaller now becomes bigger. Their outputs are going to be bigger. And this portion of the graph is increasing, so what's smaller remains smaller, right? Smaller input correspond to smaller output for increasing functions, as we learned in earlier section. And for decreasing functions, smaller inputs correspond to bigger outputs. Correct? So what I'm saying here is that this can be thought of as b, and this can be thought of as a, but both of them are non-negative, right? They're both bigger than or equal to 0. 3 is bigger than or equal to 0. So you can think about a as being 3, and the b as being the square root of x minus 3. Correct? 3 is bigger than or equal to 0. So we're talking about this part. We're talking about the purple part. And as such, we get the inequality sign remains the same. Right? We don't have to reverse it. Make sense? So this is a very important discussion here that's gonna allow me to write that this is actually equivalent to saying that the square of this guy, right, is greater than or equal to the square of this guy, which is, let me just keep it 3 squared and then we discuss it. And this equivalence is coming from the discussion right below, right? So how about we actually close this in a bubble and refer to it right there. So this equivalence is coming from the discussion just made here. Okay? And now let's keep unraveling what this means in terms of x. What does this mean in terms of x? That's equivalent to saying that what's the square of a square root? That's just the radicand. So x minus 3 is greater than or equal to 3 squared, which is 9, right? Correct? So 3 squared is 9. And that's the same thing as saying that x is greater than or equal to 12. By adding 3 to both sides, you get x is at least 12. Correct? So this blue inequality here, I know exactly what demands it places on x. It places this demand. X is at least 12. Okay? Alright, so now I'm gonna go back and complete this set. Now I have a full knowledge of it. So this is then the collection of all real numbers that are from 3 onward, right? This part, the brown one, such that x is at least 12. Correct? Such that x is at least 12. Let's put a separator here. Okay. Alright, so now take a look. The domain of the G composed with G is the collection of all numbers that are from 3 onward such that they are from 12 onward. So there is a redundancy here, obviously, right? So all real numbers that are from 3 onward and those numbers that are from 12 onward, this is the same thing as saying that you are only asking for those numbers to be from 12 onward, right? So this is then the collection of all real numbers that are all real numbers that are from 12 onward, correct? Again, there is a redundancy. If you ask for the participants in the domain of G composed with G to be from 12 onward, you've already fulfilled this demand. There is a redundancy. You don't have to ask for this. You get it for free, correct? Okay. So what's the domain of G composed with G then? It's the collection of all real numbers that are from 12 onward. And how do you interpret this using interval notation just to answer the question? This is simply the interval that's close at 12 and all the way to infinity. Yes? So this is the domain of G composed with G. Alright, and finally we have to give a recipe for G composed with G. So we have to give a recipe for the output. Well, G composed with G acting at X, and this X should live in the domain, right, of G composed with G. So we know what the domain is by now. So for X that lives in the domain of G composed with G, meaning for those x's which are from 12 onward, right, that are bigger than or equal to 12, we can find their outputs, right? And what's the output? It's gonna be G composed with G acting at X, which is equal to G acting at G of X, right? Correct? So G of X is gonna produce an output, it's gonna send it back to the function G, and the full output is gonna be the output of the composite function. Okay, so what's g of x? What's g of x? Let's color this in a different color here. Let's use pink. So what's g of x? G of x was square root of x minus 3, right? G of x is square root of x minus 3. Let's keep it in pink. So square root of x minus 3. Now the square root of x minus 3 is going to be sent again to the function g, right? So let's again revisit what the function g is. G of an input is the square root of the input minus 3, correct? That's what the function is. Who's my input now? That's my input. So g of star is square root of star minus 3. Who's my star? It's the pink expression. It's that guy, right? So what do we get? We get that this is equal to g of, let me just erase the star. So g of, oh, sorry. One more time. I'm going to erase the star. G of star is again the square root of the star, which is the square root of x minus 3, minus the 3, correct? That's my star. That's my pink guy, correct? That's my pink guy. And this would be the final recipe of the output if you input x and g compose with g. Okay? And what's the domain of this function? I mean, it's very ugly, but it is what it is. And the domain of this function is the collection of all real numbers that are from 12 all the way to infinity. All right? So this finishes the lecture video on this section, which was about algebra functions and function composition.